While the entire world fixates on 3i Atlas, the interstellar wanderer making headlines across every news platform, something far more immediate and potentially dangerous is racing toward us through the darkness of space. In just 9 days, on October 20th, 2025, an object will streak past Earth at a distance that should make every space agency administrator lose sleep. But here's the problem. Almost nobody is talking about it. You see, we've been conditioned to fear the exotic, the mysterious, the visitors from beyond our solar system. 3i Atlas captures our imagination because it originated from another star, because it carries the romance of deep space exploration, because it represents everything unknown about our cosmic neighbourhood. Meanwhile, the real threat approaches from our own backyard, and it nearly escaped detection entirely. This isn't about panic. This isn't about preparing for doomsday. This is about understanding how fragile our cosmic early warning system really is, and how the most dangerous objects aren't always the ones making headlines. By the end of this investigation, you'll understand why the scariest visitors are often the ones we don't see coming until it's almost too late. If you're ready to dive deep into a story that reveals the gaps in our planetary defense network, hit that subscribe button and let me know in the comments where you're watching from and whether you think we're being told the complete truth about cosmic threats. Your engagement helps us continue investigating the stories that matter most. Let me introduce you to C2025 R2, designated SWAN after the solar wind instrument that discovered it. While 3i Atlas maintains a comfortable distance of 1.8 astronomical units from Earth, approximately 167 million kilometers away, R2 will approach at just 0.26 astronomical units. That translates to roughly 39 million kilometers, which might sound safe until you realise this represents less than 1/4 the distance 3i Atlas maintains from our planet. But distance isn't the only concern. The story of how we discovered R2 reveals everything wrong with our current detection capabilities. This comet wasn't found by any of the sophisticated ground-based telescopes scanning our skies every night. It wasn't detected by the automated survey systems designed specifically to catch approaching objects. Instead, it was discovered by an amateur astronomer named Vladimir Bazugi, who was analysing ultraviolet data from a spacecraft instrument never intended for comet hunting. The reason R2 evaded detection for so long exp in our planetary defense strategy. Theases, a fundamental weakness comet, spent weeks hidden in what astronomers call the solar glare zone, that cone of invisibility surrounding the sun where Earth-based telescopes simply cannot observe. Objects in this region become ghosts, existing but remaining completely invisible to our most advanced detection networks. R2 passed its closest point to the sun on September 12, 2025, at a distance of roughly 75 million kilometers. During this perihelion passage, when comets typically become most active and visible, R2 remained hidden behind the sun's overwhelming brightness. By the time it emerged from this blind spot, it was already racing outward toward Earth's neighbourhood, giving us minimal time to study its behaviour and characteristics. The discovery method itself tells a troubling story about our detection capabilities. The SOHO spacecraft's SWAN instrument detects hydrogen emissions in ultraviolet light, revealing the massive hydrogen clouds that surround active comets. These clouds extend far beyond the visible coma, making them detectable even when optical telescopes see nothing. Bazugi spotted a moving blob in SWAN's archived data, a diffuse cloud that shifted position over time, indicating an active comet releasing water vapour that breaks down into hydrogen and oxygen under solar radiation. This discovery pathway represents both a triumph of citizen science and a failure of institutional surveillance. While we celebrate the dedication of amateur astronomers who analyse spacecraft data in their spare time, we must acknowledge the uncomfortable reality that our primary detection network missed an object approaching Earth until it was practically on our doorstep. The implications extend far beyond R2 itself. If a comet can hide in solar glare for weeks, emerging only after perihelion with minimal warning, how many other objects might be following similar paths? How many visitors pass through our inner solar system completely undetected because they approach from the wrong angle at the wrong time with the wrong brightness characteristics? R2's behaviour since discovery adds another layer of concern to an already troubling situation. In late September, observers recorded a sudden brightening event, with the comet jumping from relative obscurity to magnitude 5.9, making it visible through binoculars from dark sky locations. This outburst suggests internal instability, possibly indicating that volatile materials within the nucleus built up pressure and released explosively. Comet outbursts aren't unusual by themselves, but they can signal the beginning of fragmentation events. When internal pressure exceeds the structural integrity of a loosely bound nucleus, chunks can break away, each following slightly different trajectories. These fragments spread out over time, creating debris streams that can persist for years or decades along the comet's orbital path. The spectroscopic observations reveal R2 displaying the classic green coloration associated with diatomic carbon molecules fluorescing under ultraviolet sunlight. This indicates active sublimation of carbon-bearing compounds, suggesting the nucleus contains substantial volatile materials that continue outgassing as the comet moves away from the Sun. More concerning are the reported asymmetries in the tail structure. Rather than the smooth, symmetric tail typical of well-behaved comets, R2 shows streamers and jets pointing in different directions. These features suggest localized outgassing from specific vents on the nucleus surface, indicating an irregular, possibly unstable internal structure. The dust retention characteristics observed in R2's coma point toward the production of large particles rather than fine dust grains. When comets shed primarily small particles, solar radiation pressure quickly sweeps them into smooth, well-defined tails. Large particles resist this pressure, creating diffuse, slowly expanding clouds around the nucleus. The presence of large particles often indicates surface erosion or fragmentation, where chunks of nucleus material break away and continue sublimating independently. Current orbital calculations place R2's minimum orbit intersection distance with Earth at approximately 7 million kilometers. This represents the smallest possible gap between the comet's trajectory and Earth's orbital path, calculated purely from geometric considerations without regard to timing. While this sounds like a comfortable margin, it becomes less reassuring when considering the possibility of fragment dispersal. The orbital characteristics reveal R2 as a long-period comet, probably originating from the Oort cloud with an orbital period estimated at over 22,000 years. This means R2 last visited the inner solar system during the late Paleolithic period, when humans were developing agriculture and building the first permanent settlements. Such long-period comets spend most of their existence in the frigid outer reaches of the solar system, accumulating damage from cosmic radiation and interstellar dust impacts. When these ancient wanderers finally return to the Sun's vicinity, they often behave unpredictably. Their surfaces have been processed by millions of years of radiation, creating complex chemical and physical changes that affect how they respond to solar heating. Some develop insulating crusts that suppress volatile release until sudden breakthrough events trigger explosive outbursts. Others fragment gradually, shedding pieces that spread along their orbital paths. The timing of R2's discovery relative to its closest Earth approach creates a narrow observation window that limits our ability to fully characterize the object. Unlike well-known periodic comets that we can study across multiple apparitions, R2 offers just this single opportunity to understand its composition, structure, and behavior patterns. If we miss crucial observations during this passage, we lose that information forever. Professional observatories worldwide have begun coordinating observations to maximize the scientific return from R2's appearance. SPEC to determine the precistoscopic analysis aims composition of outgassing materials, while high-resolution imaging attempts to resolve the nuclear structure and detect any fragmentation. Radar observations, if the comet approaches within range of planetary radar systems, could provide direct measurements of nucleus size, rotation rate, and surface properties. The amateur astronomy community has mobilized to contribute observations using modest equipment. Backyard astronomers with telephoto lenses and small telescopes can track R2's brightness variations, documenting outburst events and tail development that professional facilities might miss due to scheduling constraints. This distributed observation network often catches transient phenomena that occur between scheduled professional observations. However, the fundamental challenge remains unchanged. We discovered R2 late in its approach, missed its perihelion passage entirely, and now face the reality of trying to understand a potentially hazardous object with incomplete information. The comet's brightness predictions remain uncertain, with estimates ranging from naked eye visibility to requiring binoculars depending on future activity levels. The broader implications of R2's late discovery extend beyond this single object to encompass systemic weaknesses in our planetary defense capabilities. Our detection network, optimized for finding objects in specific regions of the sky under ideal conditions, struggles with visitors that don't follow predictable patterns. Objects approaching from solar direction, arriving during bad weather, or brightening suddenly after initial surveys have moved on can slip through our detection grid entirely. This represents a fundamental challenge in cosmic hazard mitigation. We've built systems designed to catch the predictable threats, while remaining vulnerable to the unpredictable ones. R2 demonstrates that the most dangerous objects might not be the exotic interstellar visitors that capture headlines, but the solar system natives that hide in plain sight until they're practically at our doorstep. As we approach R2's closest passage on October 20th, the astronomical community faces a critical test of our observational capabilities and risk assessment procedures. The data we collect during these final days will determine whether this comet represents an isolated curiosity or a harbinger of more serious detection failures yet to come. The detection machinery we've constructed over decades of astronomical advancement reveals its true limitations when confronted with objects like R2. While we celebrate our ability to track thousands of near-Earth asteroids and predict their movements years in advance, we simultaneously demonstrate profound blindness to threats that refuse to follow our observational conventions. This paradox exposes the uncomfortable truth that our planetary defense network operates more like a well-calibrated fishing net than a comprehensive security system. Consider the stark contrast between how we discovered R2 and how we typically find potentially hazardous objects. The Catalina Sky Survey, Linear and NEOWISE programs methodically scan predetermined regions of sky, building catalogues of moving objects through repeated observations. These systems excel at detecting objects that behave predictably, maintaining steady brightness levels while following gravitational trajectories that conform to mathematical models. They struggle catastrophically when objects deviate from these expectations. R2's hydrogen signature in SWAN data represents detection through an entirely different physical mechanism than optical surveys employ. While ground-based telescopes rely on reflected sunlight, SWAN observes ultraviolet emissions from hydrogen atoms liberated by water vapor photodissociation. This creates a detection pathway that operates independently of traditional brightness thresholds and viewing geometry constraints. The fact that an amateur astronomer succeeded where professional surveys failed illustrates how narrow our primary detection channels have become. The geometric constraints that hid R2 from optical detection affect far more objects than most people realize. The solar exclusion zone extends roughly 30 degrees on either side of the Sun's position, creating a moving blind spot that sweeps across the sky throughout the year. Objects with certain orbital inclinations and approach vectors can remain within this zone for weeks or months, completely invisible to Earth-based telescopes regardless of their intrinsic brightness or potential danger. Space-based observations offer partial solutions to this geometric blindness, but our current space telescope fleet wasn't designed primarily for hazard detection. The Hubble Space Telescope, James Webb Space Telescope, and other flagship missions focus on distant astronomical phenomena rather than nearby solar system objects. While they can observe comets and asteroids when specifically targeted, their limited fields of view and precious observing time make them unsuitable for systematic survey work. The NEOWISE mission demonstrated the value of dedicated space-based surveys, discovering thousands of asteroids and comets during its extended operation. However, NEOWISE operates in infrared wavelengths, detecting thermal emission rather than reflected light. This provides advantages for finding dark objects with low albedos, but creates different detection biases. Objects with unusual thermal properties or compositions might evade infrared detection, just as they evade optical surveys. More troubling is our reliance on statistical assumptions about the population of potentially hazardous objects. Current risk models assume we've detected most large near-Earth asteroids and a representative sample of smaller ones. These models extrapolate from known populations to estimate the number of undiscovered objects and their impact probabilities. R2's late discovery suggests these statistical models might underestimate the population of objects that evade our primary detection methods. The discovery circumstances also highlight the crucial role of citizen scientists in modern astronomy. Vladimir Bazugi's analysis of SWAN data represents thousands of hours of volunteer effort by amateur astronomers worldwide who process spacecraft observations, search for transient phenomena, and contribute to our understanding of solar system dynamics. This distributed network often catches events that professional astronomers miss due to time constraints and institutional priorities. However, relying on volunteer efforts to catch objects that professional surveys miss represents a systemic failure rather than a triumph of citizen science. While we should celebrate amateur contributions, we cannot build planetary defense strategies around the hope that dedicated individuals will notice what our primary systems overlook. The detection network needs redundancy, multiple independent pathways that catch objects through different physical mechanisms and observational approaches. R2's outburst behavior adds complexity to an already challenging detection problem. Comets that remain dormant during their approach phase can suddenly brighten by several magnitudes when volatile materials begin sublimating or when structural failures trigger explosive outgassing. These brightness changes can occur over hours or days, faster than survey telescopes typically revisit the same sky regions. An object below detection thresholds during one observation might become easily visible days later, but only if someone happens to look at the right location at the right time. The fragmentation scenario presents perhaps the most serious long-term concern raised by R2's discovery. When comets break apart, the resulting fragments follow slightly different trajectories that diverge over time. These fragment clouds can spread across millions of kilometers, creating diffuse hazard zones rather than single-point threats. Earth's passage through such a debris field might produce meteor storms, satellite damage, or in extreme cases, multiple small impacts scattered across the planet's surface. Current orbital monitoring systems track individual objects rather than debris clouds, creating another detection gap. If R2 fragments during its current passage, the pieces might remain too close together to resolve as separate objects initially. By the time they spread sufficiently to appear as distinct targets, they could have diverged enough to create multiple intersection possibilities with Earth's orbit. The computational challenge of tracking thousands of small fragments exceeds current catalogue capabilities. The temporal aspects of R2's approach reveal additional weaknesses in our response protocols. Discovery on September 11th left approximately 5 weeks before closest approach, barely enough time for detailed characterization studies. Professional telescopes require months of advanced scheduling for major observing campaigns. Target of opportunity programs exist for urgent observations, but compete with other high-priority research for limited telescope time. The compressed timeline forces astronomers to make rapid decisions about which observations provide the most critical information. Spectroscopic analysis requires specific instrumental configurations and observing conditions that might not be immediately available. High-resolution imaging needs precise tracking capabilities and optimal seeing conditions. Radar observations demand careful coordination between transmitting and receiving facilities. Each observation type provides different information about the comet's properties, but scheduling constraints might prevent comprehensive characterization before the object moves beyond optimal observation geometry. The brightness evolution predictions for R2 illustrate another source of uncertainty in comet observations. Unlike asteroids, which follow predictable brightness curves based on distance and phase angle, comets can brighten or fade unpredictably as their activity levels change. Volatile materials have different sublimation temperatures and rates, creating complex brightness patterns that depend on nucleus composition, structure, and thermal history. Predicting whether R2 will become naked-eye visible or fade below binocular thresholds requires understanding internal properties that remain largely unknown. Weather introduces additional complications for ground-based observations. October weather patterns in both northern and southern hemispheres can limit observing opportunities through cloud cover, atmospheric turbulence, and seasonal daylight changes. Critical observations might be lost to weather during the narrow window when R2 remains optimally positioned for study. Space-based telescopes avoid weather constraints but have limited availability and different operational constraints. The communication protocols surrounding R2's discovery and tracking demonstrate both strengths and weaknesses in our scientific information sharing systems. The Minor Planet Center rapidly disseminated orbital elements and observation coordinates, enabling worldwide tracking efforts within days of confirmation. However, the technical nature of these communications limits public understanding of the object's significance and potential implications. Risk communication becomes particularly challenging when dealing with uncertain probabilities and speculative scenarios. Stating that R2 poses minimal direct impact risk while acknowledging fragmentation possibilities and detection system limitations requires nuanced messaging that often gets lost in simplified media coverage. the tendency to either dismiss objects as completely safe or sensationalize them as existential threats leaves little room for discussing the complex probability distributions that characterize real cosmic hazards. The institutional response to R2 reflects broader challenges in coordinating international space situational awareness. While astronomical organizations share observational data freely, hazard assessment and response planning involve national security considerations that complicate information sharing. Different countries maintain separate tracking capabilities and risk assessment methodologies, potentially leading to divergent conclusions about the same object. As R2 continues its approach toward the October 20th encounter, each night of observations adds crucial data points to our understanding of this enigmatic visitor. The comet's behavior during these final days will either validate our current risk assessments or force us to confront uncomfortable truths about the limitations of our cosmic early warning systems. Either outcome provides valuable lessons for improving our planetary defense capabilities before the next unexpected visitor arrives. The trajectory mathematics tell a story that should make every space agency administrator reconsider their detection priorities. While R2 maintains its current course toward the October 20th encounter, the orbital mechanics reveal troubling possibilities that extend far beyond simple distance calculations. The minimum orbit intersection distance of 7 million kilometers sounds reassuring until you factor in the uncertainty margins that accompany late discovery objects. Every orbital calculation carries error bars, statistical ranges that reflect the precision of available observations. For well-tracked objects observed across multiple apparitions, these uncertainties shrink to negligible levels. We can predict where Halley's Comet will be decades in advance, because centuries of observations have refined its orbital elements to extraordinary precision. R2 enjoys no such observational luxury. The comet's orbital solution relies on roughly 6 weeks of position measurements, a fraction of its 22,000-year orbital period. Small measurement errors, atmospheric refraction effects, and instrumental calibration uncertainties combine to create position uncertainties that grow larger as we project the orbit forward. What appears as a 7 million kilometer missed distance today could shift by hundreds of thousands of kilometers as additional observations refine the trajectory. More concerning are the non-gravitational forces that affect comet orbits in ways that pure gravitational models cannot predict. When volatile materials sublimate from the nucleus surface, the escaping gas creates tiny rocket-like forces that gradually alter the comet's path. These accelerations are small but persistent, accumulating over months to produce measurable trajectory changes. For R2, the outburst activity observed in late September indicates vigorous outgassing that almost certainly affects its trajectory. The direction and magnitude of these forces depend on the rotation state of the nucleus, the location of active vents, and the composition of escaping materials. Without detailed knowledge of these parameters, orbital predictions carry inherent uncertainties that could shift the closest approach distance by significant margins. The fragmentation scenario transforms these orbital uncertainties from academic concerns into potential hazards. If R2's nucleus splits into multiple pieces, each fragment follows a slightly different trajectory based on the velocity imparted during separation. A gentle split might produce fragments with velocity differences of just a few meters per second. Over the remaining weeks before closest approach, these small velocity differences translate into separation distances of thousands of kilometers. Historical precedents demonstrate how dramatically fragmentation can alter comet behavior. Comet Shoemaker-Levy 9 broke apart during a close encounter with Jupiter in 1992, creating a string of fragments that spread along the orbital path. When these pieces eventually collided with Jupiter 2 years later, they struck the planet over several days as a sequential bombardment rather than a single impact. Comet 73P, Schwarzmann-Wachmann experienced multiple fragmentation events, first splitting in 1995 and fragmenting again in 2006. Each breakup created new debris streams with slightly different orbital characteristics. Earth has encountered some of these debris streams in subsequent years, producing enhanced meteor activity as particles burn up in our atmosphere. The dust production mechanisms operating in comets like R2 create another layer of hazard that persists long after the parent object departs. Every gram of material ejected from the nucleus carries momentum that affects both the fragment and the parent body. Larger chunks maintain trajectories close to the original orbit, while smaller particles spread more widely due to radiation pressure and other forces. These dust grains travel at velocities measured in tens of kilometers per second relative to Earth. At such speeds, even microscopic particles carry tremendous kinetic energy. A dust grain the size of a pea travelling at 30 kilometers per second delivers energy equivalent to a hand grenade explosion. Larger particles, pebble-sized or bigger, become potentially devastating projectiles. The International Space Station operates at an altitude where collision with even small debris particles poses serious risks. The station's multi-layer shielding can stop most micrometeoroid impacts, but dense particle streams can overwhelm protective systems. During predicted meteor showers, the station sometimes adjusts its orientation to minimize cross-sectional area exposed to incoming particles. Commercial satellite constellations face similar vulnerabilities multiplied across thousands of individual spacecraft. The growing population of satellites in low Earth orbit creates an expanding target array for any debris stream that intersects our planet's vicinity. Unlike crewed spacecraft, most satellites lack protective shielding and cannot maneuver quickly to avoid incoming threats. The detection challenge becomes exponentially more complex when dealing with fragmented objects rather than single targets. Current catalogues track approximately 35,000 objects in Earth, orbit larger than 10 centimeters, but estimates suggest millions of smaller fragments remain untracked. Adding thousands of new debris pieces from a fragmenting comet would strain monitoring systems already operating near capacity limits. Ground-based radar systems can detect and track objects down to approximately 1 centimeter in size under ideal conditions, but coverage remains limited by geography, weather, and competing priorities. Space-based sensors offer some advantages, but operate with even more restricted coverage areas and observation time constraints. The computational requirements for tracking multiple fragments with uncertain trajectories quickly overwhelm current prediction systems. Each object requires individual orbital calculations updated as new observations become available. Multiply this by potentially hundreds or thousands of fragments, and the processing demands exceed available computational resources. Risk assessment becomes similarly complex when dealing with statistical hazards rather than single-point threats. Traditional impact probability calculations assume a single object with a well-defined trajectory and uncertainty envelope. Fragment clouds create diffuse threat zones where individual impact probabilities remain low, but aggregate risks across all fragments might be significant. Insurance and risk management industries struggle to quantify such distributed hazards. How do you price satellite insurance when facing an uncertain number of fragments with unknown size distributions following imprecisely known trajectories? The mathematical tools for handling single-object risks break down when confronted with cloud-based threats. The observational campaign targeting R2 during its final approach weeks represents a critical test of our rapid response capabilities. Professional observatories have allocated precious telescope time for spectroscopic analysis, hoping to determine the precise composition of outgassing materials. Different volatile compounds sublimate at different rates and temperatures, providing clues about internal structure and fragmentation likelihood. High-resolution imaging attempts to resolve the nuclear structure directly, searching for signs of existing fractures or surface features that might indicate structural weaknesses. The challenge lies in distinguishing genuine nucleus features from Comet artifacts created by surrounding gas and dust clouds. Photometric monitoring tracks brightness variations that could indicate rotational tumbling, outburst activity, or fragment separation events. Amateur astronomers contribute crucial coverage by monitoring the comet continuously across different time zones and weather conditions. Their distributed observations often catch transient events that scheduled professional observations might miss. Radar observations offer the potential for direct ranging measurements that could dramatically improve orbital accuracy. However, R2's distance and relatively small size push radar capabilities to their limits. Only the most powerful planetary radar systems have any chance of detecting returns from the comet's nucleus. The data collected during these intensive observations will determine whether R2 represents an isolated anomaly in our detection capabilities or a representative example of how many objects slip through our surveillance network unnoticed. The answer to that question has profound implications for how we assess our current level of planetary protection. Theoretical models suggest that the solar system contains millions of comet-sized objects in the outer regions, with a small fraction following orbits that bring them into the inner system periodically. If our detection system miss a significant percentage of these visitors, Our risk assessments based on observed populations dramatically underestimate the true hazard rates. The timing coincidence of R2's discovery relative to the intense media focus on 3I Atlas raises uncomfortable questions about attention allocation and resource distribution. While the astronomical community mobilizes to study an interstellar visitor that poses no conceivable threat to Earth, a potentially more relevant object approaches with minimal public awareness or institutional focus. This mismatch between newsworthiness and actual hazard significance reflects broader challenges in science communication and risk prioritization. Exotic phenomena capture public imagination, and funding support more easily than mundane but potentially dangerous objects from our own cosmic neighborhood. The lessons learned from R2's approach will inform future detection strategies and resource allocation decisions. Whether those lessons validate current approaches or demand fundamental changes depends on what the next few days of observations reveal about this enigmatic visitor from the outer darkness. The cascading effects of delayed detection extend far beyond the immediate concerns surrounding R2's trajectory. When we examine the broader landscape of cosmic surveillance, a disturbing pattern emerges that challenges our fundamental assumptions about planetary security. The infrastructure we've constructed to protect Earth operates on principles that work beautifully under ideal conditions, but collapse catastrophically when reality refuses to cooperate. Our detection network resembles a sophisticated early warning system designed by engineers who assumed threats would announce themselves politely and arrive from predictable directions. The reality proves far more chaotic. Objects hide in solar glare, brighten unexpectedly after surveys have moved on, approach from angles that place them in geometric blind spots, or simply remain too faint to trigger automated detection algorithms until they're practically at our doorstep. The statistical models underlying our risk assessments depend critically on the assumption that we've detected a representative sample of the total population. If systematic biases in our detection methods cause us to miss entire categories of objects, our probability calculations become exercises in mathematical fiction. We might be dramatically underestimating hazard rates while congratulating ourselves on the completeness of our catalogues. Consider the implications if R2 represents not an anomaly, but a typical example of how many objects approach Earth undetected. Current estimates suggest we've identified roughly 90% of near-Earth asteroids larger than 1 kilometer in diameter. This statistic sounds reassuring until you realize it's based on extrapolations from observed populations. If our detection methods systematically miss objects with certain characteristics, that 90% figure might be wildly optimistic. The economic dimensions of this detection gap carry staggering implications for modern civilization. The satellite industry alone represents hundreds of billions of dollars in orbital infrastructure supporting everything from global communications to financial transactions to military operations. A single debris cloud intersecting Earth's orbital space could damage or destroy satellites worth tens of billions of dollars, while disrupting services that billions of people depend on daily. Ground-based infrastructure faces different but equally serious vulnerabilities. While the atmosphere shields us from most small particles, larger fragments can survive to impact the surface with devastating consequences. The 2013 Chelyabinsk meteor, roughly 20 meters in diameter, exploded in the atmosphere with energy equivalent to several hundred kilotons of TNT, shattering windows across a city and injuring over 1,000 people. That object arrived without warning, detected only as it blazed across the sky. Insurance markets have begun grappling with these distributed risks, but the mathematical tools for pricing such hazards remain primitive. How do you calculate premiums when facing uncertain numbers of fragments, with unknown size distributions following in precisely determined trajectories? Traditional actuarial models assume well-defined risks with historical precedents. Fragmenting comets create novel hazard categories that exceed the boundaries of conventional risk analysis. The international coordination challenges become exponentially more complex when dealing with fragmented objects rather than single targets. Different countries maintain separate tracking capabilities with varying levels of accuracy and coverage. Sharing data about thousands of small fragments requires communication protocols that don't currently exist, and computational resources that strain available systems. Military space surveillance networks possess capabilities that far exceed civilian astronomical surveys, but classification restrictions limit how this information can be shared with the broader scientific community. The most sensitive tracking systems remain classified, creating information asymmetries that complicate coordinated response efforts. Civilian astronomers might be tracking objects that military sensors have already catalogued, but security classifications prevent data sharing that could improve orbital predictions. The temporal constraints surrounding R2's observation window highlight another systemic weakness in our response capabilities. Professional telescopes require months of advanced scheduling for major observing campaigns. Target of opportunity programs exist for urgent observations, but they compete with other high-priority research for limited telescope time. The compressed timeline between discovery and closest approach forces astronomers to make rapid decisions about which observations provide the most critical information. Spectroscopic analysis demands specific instrumental configurations and optimal observing conditions that might not be immediately available. Weather patterns during October could limit ground-based observations through cloud cover and atmospheric turbulence. Space-based telescopes avoid weather constraints but operate with even more restricted availability and scheduling inflexibility. The brightness prediction uncertainties surrounding R2 illustrate fundamental challenges in comet observation and characterization. Unlike asteroids, which follow predictable brightness curves based on distance and phase angle, comets can brighten or fade unpredictably as their activity levels change. Volatile materials sublimate at different rates, depending on nucleus composition, internal structure, and thermal history. Current estimates suggest R2 might reach magnitude 4 under optimal conditions, making it easily visible to the naked eye from dark sky locations. More conservative predictions place it around magnitude 6, requiring binoculars for observation. The uncertainty reflects our limited understanding of the comet's internal properties and outgassing characteristics. Amateur astronomers worldwide have mobilized to contribute observations using backyard telescopes and camera systems. This distributed network often catches transient phenomena that professional facilities miss due to scheduling constraints. Dedicated observers monitor the comet continuously across different time zones, providing crucial coverage that no single observatory could match. However, the quality and calibration of amateur observations varies significantly. While many dedicated amateurs maintain equipment and techniques rivaling professional standards, others produce measurements with large uncertainties that can introduce errors into orbital calculations. Distinguishing reliable observations from problematic data requires careful analysis and cross-validation. The social media landscape surrounding R2's approach demonstrates both the potential and perils of modern science communication. Accurate information about the comet's trajectory and characteristics competes with sensationalized claims about impact risks and conspiracy theories about institutional cover-ups. The compressed timeline between discovery and closest approach leaves little time for thorough peer review and scientific consensus building. Misinformation spreads faster than correction in digital environments, optimized for engagement rather than accuracy. Dramatic claims about comet fragments or hidden dangers generate more social media interaction than measured discussions of orbital mechanics and probability distributions. The result is a public discourse that often bears little resemblance to the actual scientific understanding of the situation. Educational institutions face challenges in rapidly incorporating new discoveries into curricula and public outreach programs. R2's late discovery left little time for developing educational materials or coordinating with planetariums and science museums. The compressed timeline limits opportunities for using the comet's approach as a teaching moment about planetary defense and astronomical observation techniques. The psychological dimensions of cosmic hazard perception create communication, human cognition, additional complications for riskation, evolve to assess immediate visible threats rather than statistical risks distributed across vast spatial and temporal scales. People struggle to calibrate their responses to low-probability, high-consequence events, often oscillating between complete dismissal and paralyzing anxiety. Media coverage patterns amplify these psychological biases by focusing on dramatic narratives rather than nuanced probability discussions. Headlines emphasizing monster comets or civilization-ending threats capture attention but distort public understanding of actual risk levels. Conversely, overly technical discussions of orbital mechanics and statistical uncertainties can make genuine hazards seem abstract and irrelevant. The resource allocation decisions facing space agencies reflect broader challenges in balancing competing priorities with limited budgets. Detecting and tracking near-Earth objects requires sustained investment in survey telescopes data processing systems, and analysis personnel. These capabilities develop slowly over decades but can be compromised quickly by budget cuts or shifting political priorities. Current detection systems represent the accumulated investment of multiple generations of astronomers and engineers. The survey telescopes scanning our skies tonight were planned and funded years or decades ago. Upgrading these capabilities to address newly recognized gaps requires long-term commitments that extend beyond typical political cycles. The Vera Rubin Observatory, scheduled to begin operations in the coming years, promises to revolutionize our detection capabilities by scanning the entire visible sky every few nights. This next-generation facility will discover objects at unprecedented rates, but it also inherits the geometric limitations that affect all ground-based systems. Objects approaching from solar direction will remain invisible regardless of telescope capability. Space-based detection systems offer solutions to some geometric constraints, but introduce new challenges related to cost, complexity, and operational lifetime. Spacecraft missions require years of development and testing before launch, followed by years of travel time to reach operational positions. The technological and financial barriers to deploying comprehensive space-based surveys exceed current institutional capabilities. International cooperation offers potential pathways for sharing the costs and benefits of improved detection systems, but coordination across different space agencies involves complex negotiations about data sharing, cost allocation, and operational control. Previous collaborative efforts have achieved remarkable successes, but required decades to plan and implement. The scientific return from studying R2 during its current passage will inform future detection strategies and risk assessment methodologies. Every observation adds crucial data points to our understanding of how comets behave during close approaches to Earth. The lessons learned will influence how we design next-generation survey systems and allocate resources for planetary defense initiatives. As October 20th approaches, the astronomical community faces a critical test of our rapid response capabilities and international coordination mechanisms. The data collected during these final days will either validate current detection strategies or expose fundamental weaknesses that demand immediate attention and resources. The broader implications extend far beyond this single object to encompass our entire approach to cosmic hazard mitigation. R2's late discovery and uncertain characteristics represent a case study in the challenges facing planetary defense efforts. Whether we learn the right lessons from this encounter could determine how well prepared we are for the next unexpected visitor from the outer darkness. The detection machinery we've constructed reveals its limitations most clearly when confronted with objects that refuse to follow our observational conventions. While we celebrate our ability to predict asteroid positions years in advance, we simultaneously demonstrate profound blindness to threats approaching from inconvenient angles at inconvenient times, with inconvenient characteristics that don't match our automated detection algorithms. This paradox exposes uncomfortable truths about the assumptions underlying our planetary defense network. We've optimized for finding predictable objects while remaining vulnerable to the unpredictable ones. The most dangerous visitors might not be the exotic interstellar wanderers that capture headlines, but the solar system natives that hide in plain sight until they're practically at our cosmic doorstep. The orbital mechanics governing R2's approach reveal complexities that extend far beyond simple distance calculations. While current models predict a safe passage at 39 million kilometers, the mathematical uncertainties embedded within these predictions tell a more nuanced story. Every comet carries what astronomers call non-gravitational forces, subtle accelerations created when volatile materials escape from the nucleus surface. These tiny rocket-like effects accumulate over time, gradually shifting trajectories in ways that pure gravitational models cannot anticipate. For a comet discovered just weeks before closest approach, these uncertainties matter enormously. R2's outburst activity in late September confirms vigorous outgassing that almost certainly affects its trajectory. The direction and magnitude of these forces depend on factors we cannot directly observe: the rotation state of the nucleus, the location of active vents, the composition of escaping materials. Without detailed knowledge of these parameters, our orbital predictions carry inherent margins of error that could shift the closest approach distance by significant amounts. The fragmentation scenario transforms these mathematical uncertainties from academic curiosities into genuine concerns. Comets don't break apart like brittle rocks shattering on impact. They separate more gradually, with internal pressure from sublimating volatiles overwhelming the weak gravitational forces holding loosely bound nuclei together. When this happens, fragments receive small velocity kicks that send them on slightly different trajectories. Consider what a gentle fragmentation event might produce. Pieces separating at just a few meters per second would spread thousands of kilometers apart by the time they reach Earth's vicinity. A more energetic breakup could scatter fragments across millions of kilometers, creating a diffuse debris field rather than a single-point threat. Each fragment follows its own trajectory, some diverging toward Earth's orbital path, others spreading harmlessly into space. The mathematical challenge of tracking multiple fragments exceeds our current computational capabilities. Modern catalogues monitor approximately 35,000 objects in Earth orbit, but most tracking systems focus on predictable satellites and well-characterized asteroids. Adding thousands of new debris pieces with uncertain trajectories would overwhelm existing monitoring networks, while creating computational demands that strain available processing power. Historical precedents demonstrate how dramatically fragmentation alters risk profiles. Comet Shoemaker-Levy 9 broke apart during a close encounter with Jupiter, creating a string of fragments that eventually bombarded the planet over several days. The impacts released energy equivalent to millions of nuclear weapons, leaving scars in Jupiter's atmosphere that persisted for months. While Earth lacks Jupiter's gravitational influence to capture and destroy incoming fragments, the principle remains the same. What begins as a single object can become a distributed threat. The dust production mechanisms operating within active comets create another layer of hazard that persists long after the parent object departs. Every particle ejected from R2's nucleus carries momentum that affects both the fragment and the remaining comet. Larger chunks maintain trajectories close to the original orbit, while smaller particles spread more widely due to radiation pressure and electromagnetic forces. These dust grains travel at velocities that transform even microscopic particles into high-energy projectiles. A fragment the size of a grain of sand traveling at 30 kilometers per second relative to Earth carries kinetic energy comparable to a bullet fired from a high-powered rifle. Scale this up to pebble-sized fragments, and you're dealing with projectiles that could punch through spacecraft hulls or damage critical satellite components. The International Space Station operates within an altitude range where collision with debris particles poses serious operational risks. The station's multi-layer shielding can stop most micrometeoroid impacts, but dense particle streams can overwhelm protective systems. During predicted meteor showers, flight controllers sometimes adjust the station's orientation to minimize cross-sectional area exposed to incoming particles. If R2 fragments and creates a debris stream that intersects Earth's orbital vicinity, similar precautions might become necessary across the entire satellite infrastructure. Commercial satellite constellations face even greater vulnerabilities due to their sheer numbers and lack of protective shielding. Thousands of communication, navigation, and Earth observation satellites occupy low Earth orbit, creating an expanding target array for any debris stream that crosses our planet's path. Unlike the International Space Station, most satellites cannot maneuver quickly to avoid incoming threats and lack the robust shielding necessary to survive high-velocity impacts. The insurance implications of distributed debris risks challenge traditional actuarial models designed for well-defined, historically precedented hazards. How do you calculate premiums when facing uncertain numbers of fragments with unknown size distributions following imprecisely determined trajectories? The satellite industry represents hundreds of billions of dollars in orbital infrastructure, but insuring against fragmenting comet debris requires mathematical tools that don't yet exist in commercial risk assessment. Detection systems optimized for tracking single objects struggle when confronted with fragment clouds containing thousands of individual pieces. Ground-based radar networks can identify objects down to approximately 1 centimeter under ideal conditions, but coverage remains limited by geographical constraints, weather patterns, and competing observational priorities. Space-based sensors offer some advantages but operate with restricted fields of view and limited observation time. The computational requirements for maintaining accurate orbital predictions across multiple fragments quickly overwhelm available processing resources. Each object requires individual calculations updated as new observations become available. Multiply this by potentially hundreds or thousands of fragments, and the XC mathematical demands current catalogue capabilities, while straining communication networks designed to handle much smaller data volumes. Weather patterns during October introduce additional complications for ground-based observations of R2's final approach. Seasonal cover cloud, atmospheric turbulence, and changing daylight hours can limit observing opportunities during the narrow window when the comet remains optimally positioned for detailed study. Critical observations might be lost to meteorological conditions during the weeks when characterizing the object's behavior becomes most crucial. Space-based telescopes avoid weather constraints but face different operational limitations. The Hubble Space Telescope and James Webb Space Telescope can provide exquisite detail when properly targeted, but their limited observing time makes fields of view and precious them unsuitable for continuous monitoring. Target of opportunity programs exist for urgent observations, but they compete with other high-priority research for extremely scarce telescope allocations. The amateur astronomy community has mobilized to fill some observational gaps using distributed networks of backyard telescopes and digital cameras. Dedicated observers across different time zones can provide continuous coverage that no single professional facility could match. Their observations often catch transient phenomena like outburst events or brightness variations that scheduled professional observations might miss entirely. However, the quality and calibration of amateur observations varies significantly across this distributed network. While many dedicated amateurs maintain equipment and techniques that rival professional standards, others produce measurements with large uncertainties that can introduce errors into orbital calculations. Distinguishing reliable observations from problematic data requires careful analysis and cross-validation that consumes valuable time and expertise. The social media landscape surrounding R2's approach demonstrates the challenges of communicating complex astronomical concepts during compressed timelines. Accurate information about orbital mechanics and probability distributions competes with sensationalized claims about impact risks and conspiracy theories about institutional cover-ups. The rapid pace of digital information sharing leaves little time for peer review processes that normally filter scientific conclusions before public release. Misinformation propagates faster than correction in online environments, optimized for engagement rather than accuracy. Dramatic headlines about monster comets or civilization-ending threats generate more clicks and shares than measured discussions of statistical uncertainties and detection limitations. The result is public discourse that often bears little resemblance to actual scientific understanding, while amplifying anxiety about hazards that may not exist. Educational institutions struggle to incorporate rapidly developing situations like into established curricula and out R2's approach reach programs. The compressed timeline between discovery and closest approach leaves insufficient time for developing educational materials or coordinating with planetariums and science museums. This limits opportunities to use the comet's passage as a teaching moment about planetary defense concepts and astronomical observation techniques. The psychological dimensions of cosmic hazard perception create additional complications for risk communication efforts. Human cognition evolved to assess immediate visible threats rather than statistical risks distributed across vast spatial and temporal scales. People find it difficult to calibrate appropriate responses to low probability, high consequence events, often oscillating between complete dismissal and paralyzing anxiety without finding middle ground. Media coverage patterns amplify these cognitive biases by focusing on narrative drama rather than nuanced probability discussions. Stories that fit familiar templates about approaching disasters or institutional incompetence receive more attention than complex explanations of orbital mechanics and uncertainty quantification. This creates information environments where genuine scientific understanding gets buried beneath layers of sensationalism and speculation. Resource allocation decisions facing space agencies reflect broader challenges in balancing competing priorities within constrained budgets. Detecting and tracking near-Earth objects requires sustained investment in survey telescopes, data processing systems, and specialized personnel. These capabilities develop slowly over decades, but can be compromised quickly by budget reductions or shifting political priorities that favor more visible projects. Current detection systems represent accumulated investments spanning multiple generations of astronomers and engineers. The survey telescopes scanning our skies tonight were planned and funded years or decades ago, based on threat assessments and technological capabilities that may no longer reflect current realities. Upgrading these systems to address newly recognized gaps requires long-term commitments that extend beyond typical political cycles while competing with other national priorities. The Vera Rubin Observatory, scheduled to begin full operations soon, promises to revolutionize detection capabilities by scanning the entire visible sky every few nights with unprecedented sensitivity. This next-generation facility will discover objects at rates that dwarf current surveys, but it inherits the same geometric limitations that affect all ground-based systems. Objects approaching from solar directions will remain invisible regardless of technological advances. Space-based detection systems offer solutions to geometric constraints, but introduce new challenges related to cost, complexity, and operational longevity. Spacecraft missions require years of development and testing before launch, followed by additional years reaching operational positions. The technological and financial barriers to deploying comprehensive space-based surveys exceed current institutional capabilities while demanding international cooperation on unprecedented scales. The scientific return from studying R2 during its current passage will inform future detection strategies and risk assessment methodologies for decades to come. Every spectroscopic observation, every brightness measurement, every image revealing coma structure adds crucial data points to our understanding of how ancient comets behave when returning to the inner solar system after millennia in the cold outer darkness. These observations face racing against time as R2 approaches its closest point on October 20th. The window for detailed characterization narrows with each passing day as the comet's changing geometry relative to Earth affects observing conditions. Solar elongation angles shift, phase angles change, and brightness levels fluctuate in ways that either enhance or degrade our ability to extract meaningful data from limited observation opportunities. Professional observatories worldwide have allocated precious telescope time for coordinated observations, despite the challenges of rapid scheduling changes and competing research priorities. Spectroscopic analysis attempts compositions of outgassing materials, while to determine precise high-resolution imaging searches for signs of structural features or fragmentation events. Each observation type provides different pieces of information necessary for comprehensive risk assessment. The coordination required for effective multi-site observations tests, international cooperation mechanisms that normally operate over much longer timescales, sharing data rapidly across different institutions, coordinating observation schedules across time zones, and maintaining communication during rapidly evolving situations requires infrastructure and protocols that weren't designed for crisis response scenarios. As we approach the critical October 20th date, every night of clear skies becomes precious for advancing our understanding of this enigmatic visitor. The data collected during these final weeks will determine whether R2 represents an isolated anomaly in our detection capabilities or a representative example of how many similar objects approach Earth unnoticed until they're practically at our cosmic doorstep. The implications extend far beyond this single comet to encompass our entire philosophical approach to planetary defense. If detection systems optimize for predictable threats remain blind to unpredictable ones, we may need fundamental reassessments of how we allocate resources and design future surveillance networks. The lessons learned from R2's passage could influence space policy decisions for generations to come. The mathematical elegance of orbital mechanics provides comforting precision in an uncertain universe, but that precision depends entirely on the completeness and accuracy of input data. When objects like R2 arrive with minimal observational history and uncertain physical properties, even the most sophisticated computational models produce results hedged with statistical uncertainties that could encompass a wide range of outcomes. These uncertainties compound when we consider the broader population of similar objects that may be approaching Earth through detection gaps we're only beginning to recognize. R2's late discovery suggests that current statistical models of near-Earth object populations may significantly underestimate the true numbers of potentially hazardous visitors. If systematic biases in our detection methods cause us to miss entire categories of objects, our risk calculations become exercises in mathematical fiction rather than reliable hazard assessments. The economic dimensions of these detection gaps carry implications that extend far beyond astronomical curiosity into the foundations of modern technological civilization. The satellite infrastructure supporting global communications, financial transactions, navigation systems, and military operations represents investments measured in hundreds of billions of dollars. A single debris cloud intersecting Earth's orbital environment could damage or destroy assets worth tens of billions, while disrupting services that billions of people depend on for daily activities. Ground-based infrastructure faces different but equally serious vulnerabilities despite atmospheric protection from smaller particles. Larger fragments can survive atmospheric passage to impact populated areas with devastating consequences. The 2013 Chelyabinsk event demonstrated how even a 20-meter object can cause widespread damage and injury when exploding above a city, shattering windows across hundreds of square kilometers and sending over 1,000 people to hospitals. That Russian incident arrived without any advance warning, detected only as it blazed across the morning sky at hypersonic velocity. The object approached from the direction of the sun, rendering it invisible to ground-based surveys until the final moments before atmospheric entry. If R2 or its potential fragments followed similar approach geometries, we might face comparable warning limitations despite decades of improvements in detection technology. The international coordination challenges multiply exponentially when dealing with distributed threats rather than single objects. Different countries maintain separate space surveillance networks with varying capabilities, coverage patterns, and data sharing policies. Military tracking systems often possess superior sensitivity compared to civilian astronomical surveys, but classification restrictions limit how effectively this information can be integrated with broader scientific efforts. Sharing data about thousands of small fragments requires communication protocols and computational infrastructure that don't currently exist at the necessary scales. The bandwidth requirements for transmitting high-frequency position updates across international networks could overwhelm existing data links while demanding processing power that strains available computational resources. The temporal aspects of R2's compressed observation timeline highlight systemic weaknesses in our institutional response capabilities that extend beyond technological limitations into organizational and procedural constraints. Professional telescopes typically require months of advanced planning for major observing campaigns, with proposal deadlines occurring seasons before actual observations. Target of opportunity programs provide some flexibility for urgent requests, but they must compete with established research priorities for limited telescope access. The bureaucratic machinery of modern astronomy wasn't designed for rapid response scenarios where critical observations must be planned, approved, scheduled, and executed within weeks rather than months or years. Peer review processes that ensure scientific quality and resource allocation fairness become obstacles when time constraints demand immediate action based on preliminary data and uncertain threat assessments. Weather introduces additional layers of complexity that can't be controlled or predicted with sufficient accuracy to guarantee observational success. October weather patterns in both northern and southern hemispheres bring increased cloud cover, atmospheric turbulence, and seasonal changes in daylight hours that limit optimal observing windows. Critical measurements might be lost to meteorological conditions during the narrow period when R2 remains positioned for detailed study. The brightness prediction uncertainties surrounding R2 reflect fundamental challenges in understanding comet behavior that persist despite decades of research into these ancient objects. Unlike asteroids, which follow predictable brightness curves based on distance, phase angle, and surface properties, comets can brighten or fade dramatically as their internal activity levels change in response to solar heating, structural evolution, or outburst events. Current estimates suggest R2 could reach magnitude 4 under optimal conditions, making it easily visible to naked-eye observers at dark sky locations. More conservative models predict it will hover around magnitude 6, requiring binoculars or small telescopes for observation. This uncertainty range reflects our limited understanding of the comet's nucleus composition, internal structure, and volatile distribution patterns. The amateur astronomy community worldwide has responded to R2's approach with remarkable dedication, deploying backyard telescopes and digital imaging systems to contribute observations that complement professional efforts. This distributed network provides continuous monitoring capability across multiple time zones and weather systems, often catching transient phenomena that scheduled institutional observations might miss entirely. However, the varying quality and calibration standards across amateur networks create data validation challenges that consume valuable analysis time. While many dedicated observers maintain equipment and techniques that approach professional standards, others produce measurements with significant uncertainties that require careful evaluation before incorporation into orbital calculations and risk assessments. The social media information environment surrounding R2's approach reveals both the potential and perils of modern science communication during developing situations. Accurate information about orbital mechanics and statistical uncertainties must compete with sensationalized content optimized for engagement rather than educational value. Dramatic claims about impact risks or institutional conspiracies generate more interaction and sharing than measured discussions of probability distributions and detection limitations. This creates feedback loops where misinformation propagates faster than correction, particularly when authoritative sources remain cautious about making definitive statements regarding uncertain outcomes. The compressed timeline between discovery and closest approach provides insufficient opportunity for the peer review and consensus building processes that normally filter scientific conclusions before public dissemination. Educational institutions face similar challenges in rapidly incorporating breaking astronomical developments into established curricula and outreach programming. The weeks between R2's discovery and closest approach provide inadequate time for developing comprehensive educational materials or coordinating with planetariums and science museums. This limits opportunities to leverage public interest in the Comet's passage for broader education about planetary defense concepts and astronomical observation techniques. The psychological aspects of cosmic hazard perception introduce additional complications that affect how effectively risk information can be communicated to diverse audiences. Human cognitive systems evolved to assess immediate visible threats rather than statistical risks distributed across vast spatial and temporal scales. People struggle to calibrate appropriate emotional and behavioral responses to low-probability, high-consequence events, often oscillating between dismissive skepticism and paralyzing anxiety. Media coverage patterns amplify these cognitive biases through narrative frameworks that emphasize dramatic conflict and resolution, rather than nuanced uncertainty and gradual knowledge accumulation. Stories about approaching cosmic threats fit familiar templates that generate audience engagement, but these templates often distort scientific understanding by demanding premature conclusions about inherently uncertain situations. The resource allocation decisions facing space agencies reflect broader institutional challenges in balancing immediate operational needs against long-term capability development within constrained budgets. Detecting and tracking near-Earth objects requires sustained investment in survey telescopes, data processing infrastructure, and specialized personnel whose expertise develops over decades of experience with these rare but critical events. Current detection capabilities represent the accumulated investment of multiple generations of astronomers, engineers, and policymakers who built systems based on threat assessments and technological possibilities that may no longer reflect contemporary realities. Upgrading these systems to address newly recognized vulnerabilities requires long-term commitments that extend beyond typical political cycles while competing with other national priorities for limited resources. The approaching launch of the Vera Rubin Observatory promises to revolutionize near-Earth object detection through unprecedented sky coverage and sensitivity levels. This next-generation facility will discover objects at rates that dwarf current surveys while providing rapid follow-up capabilities for newly detected threats. However, even this advanced system inherits fundamental geometric limitations that affect all ground-based observations. Objects approaching from solar directions will remain invisible to the Rubin Observatory regardless of its technological sophistication, creating persistent blind spots in our detection coverage. Space-based systems offer potential solutions to these geometric constraints, but they require international cooperation, sustained funding commitments, and technological development programs that span decades from initial concept to operational deployment. The scientific knowledge gained from studying R2 during its current passage will influence detection strategies, risk assessment methodologies, and resource allocation priorities for decades to come. Every measurement of its composition, structure, and behavior provides crucial data for understanding how ancient comets evolved during their rare returns to the inner solar system after millennia of dormancy in the outer darkness. These observations race against time as changing geometric relationships between R2, Earth, and the Sun affect observing conditions in ways that either enhance or degrade our ability to extract meaningful information. Solar elongation angles shift daily, phase relationships change, and brightness levels fluctuate according to complex interactions between distance, activity level, and viewing geometry. As October 20th approaches, the astronomical community faces a critical examination of our rapid response capabilities, international coordination mechanisms, and institutional flexibility in addressing unexpected cosmic visitors. The lessons learned from this encounter will either validate current approaches to planetary defense or expose fundamental weaknesses that demand immediate attention and resources. The broader implications transcend this single object to encompass our entire philosophical framework for assessing and mitigating cosmic hazards. Whether we emerge from the R2 encounter with confidence in our detection systems or recognition of their limitations will influence space policy decisions, funding priorities, and international cooperation agreements for generations of future planetary defenders. The ripple effects of R2's late detection expose vulnerabilities that cascade through every layer of our cosmic defense infrastructure like dominoes falling in slow motion. When we peel back the comfortable assumptions underlying our planetary protection systems, we discover a network optimized for catching predictable visitors while remaining catastrophically blind to the unpredictable ones that matter most. The detection bias problem extends far beyond simple geometric blind spots into the fundamental architecture of how we scan the heavens. Our automated survey systems operate on algorithms trained to recognize specific patterns of motion, brightness, and behavior. These digital sentinels excel at flagging objects that conform to expected parameters, but struggle catastrophically when reality refuses to cooperate with their programming. Consider how machine learning systems process astronomical data. Neural networks trained on thousands of typical asteroid detections learn to recognize the standard signatures of reflected sunlight, predictable motion rates, and consistent brightness levels. When R2 arrived with hydrogen emissions invisible to optical telescopes, unusual activity patterns, and an approach vector hidden in solar glare, these algorithmic gatekeepers simply filtered it out as noise. This represents a profound philosophical problem disguised as a technical limitation. We've constructed detection systems that find what we expect to find while missing what we don't anticipate. The most dangerous cosmic visitors might be precisely those that violate our assumptions about how threatening objects should behave. The computational challenge of processing astronomical data has reached scales that dwarf human comprehension. Modern wide-field surveys generate petabytes of information every year, with each image containing millions of individual measurements. No human team could possibly examine this volume of data manually, making us dependent on automated systems that operate according to rules we've programmed based on incomplete understanding. These algorithms make thousands of classification decisions every night, sorting celestial objects into categories like star, galaxy, asteroid, or noise. The accuracy rates sound impressive, until you realize that even a 99.9% success rate means thousands of objects get misclassified daily. Some of these errors involve routine catalog maintenance, but others might represent genuine hazards dismissed as instrumental artifacts or background contamination. The false positive problem creates its own cascade of complications that amplify detection failures. When automated systems flag too many non-existent threats, human reviewers develop pattern recognition shortcuts that help them process alert queues more efficiently. They learn to quickly identify and dismiss certain types of false alarms based on visual appearance, timing patterns, or instrumental characteristics. But these mental shortcuts, these heuristic filters that make human review feasible, can also screen out genuine anomalies that don't fit familiar categories. An unusual object might trigger multiple red flags that normally indicate false positives, causing reviewers to dismiss it without detailed analysis. The very efficiency mechanisms that make large-scale surveys possible can blind us to exceptional cases that demand special attention. The international data-sharing protocols that enable global coordination also introduce bottlenecks that can delay critical discoveries. When an observatory in Chile detects a potential threat, the information must flow through verification procedures, formatting standards, and communication channels before reaching colleagues in other time zones. Each step in this process adds delay while the object continues moving across the sky. Time zone coordination becomes particularly challenging for objects discovered near the horizon, where geometric constraints limit observation windows to just a few hours before the target sets below local horizons. If confirmation observations require facilities on different continents, the logistics of arranging rapid follow-up can consume precious hours when every minute of observation time matters. Weather introduces another layer of complexity that can't be predicted or controlled with sufficient accuracy to guarantee observational success. October weather patterns across major observatory sites bring increased cloud cover, atmospheric turbulence, and seasonal changes that affect optimal observing conditions. Critical measurements might be lost to meteorological factors during the narrow window when characterization becomes most urgent. The backup systems and redundancy measures built into professional observatory networks provide some protection against individual facility failures, but they can't compensate for systematic biases that affect entire classes of detection methods. If multiple independent surveys all rely on similar optical techniques, they'll all share similar blind spots and detection limitations. Space-based observations offer potential solutions to weather and geometric constraints, but they introduce different operational challenges related to scheduling flexibility and target accessibility. The Hubble Space Telescope and James Webb Space Telescope can provide exquisite detail when properly directed, but their limited fields of view and precious observing time make them unsuitable for systematic surveillance work. The amateur astronomy community has emerged as an unexpected but crucial component of our detection network, with dedicated observers using backyard telescopes to monitor objects that professional facilities might only observe occasionally. This distributed surveillance capability provides continuous coverage across multiple time zones and weather systems, often catching transient events that scheduled institutional observations miss entirely. However, the varying calibration standards and measurement uncertainties across amateur networks create data validation challenges that consume valuable analysis time. While many serious amateurs maintain equipment approaching professional standards, others produce observations with significant error bars that require careful evaluation before incorporation into orbital calculations. The economic implications of detection failures extend beyond immediate impact risks into the broader infrastructure of modern technological civilization. The satellite networks supporting global communications, navigation systems, financial transactions, and military operations represent investments measured in hundreds of billions of dollars, all potentially vulnerable to debris clouds that existing detection systems might miss until too late. Insurance markets struggle to quantify distributed risks involving uncertain numbers of fragments, with unknown trajectories and impact probabilities. Traditional actuarial models assume well-defined hazards with historical precedents, but fragmenting comets create novel threat categories that exceed the mathematical frameworks currently available for commercial risk assessment. The legal and regulatory frameworks governing space activities weren't designed to handle scenarios involving thousands of small debris pieces with uncertain ownership and liability chains. If R2 fragments and pieces damage satellites or ground facilities, determining responsibility and compensation could involve unprecedented legal challenges that current space law doesn't adequately address. International coordination mechanisms face exponential complexity increases when dealing with fragment clouds rather than single objects. Different nations maintain separate tracking capabilities with varying accuracy levels and data sharing policies. Military surveillance networks often possess superior sensitivity compared to civilian systems, but classification restrictions limit integration with broader scientific efforts. The communication bandwidth requirements for sharing high-frequency position updates across international networks could overwhelm existing data links while demanding processing power that strains available computational resources. Current catalog systems weren't designed to handle thousands of new objects appearing simultaneously, with uncertain trajectories requiring constant updates. The psychological dimensions of cosmic hazard perception create additional communication challenges that affect how effectively risk information reaches diverse audiences. Human cognitive systems evolved to assess immediate visible threats rather than statistical risks, distributed across vast spatial and temporal scales. People find it difficult to calibrate appropriate responses to low-probability, high-consequence events. Media coverage patterns amplify these cognitive limitations through narrative frameworks that demand dramatic conflict and resolution, rather than nuanced uncertainty discussions. Stories about approaching cosmic threats must fit familiar templates to generate audience engagement, but these templates often distort scientific understanding by requiring premature conclusions about inherently uncertain situations. Educational institutions face compressed timelines that prevent comprehensive curriculum development or coordination with planetariums and science museums. The weeks between R2's discovery and closest approach provide inadequate preparation time for leveraging public interest in broader education about planetary defense concepts and astronomical observation techniques. The social media information environment creates feedback loops where misinformation propagates faster than correction. particularly when authoritative sources remain appropriately cautious about uncertain outcomes. Dramatic claims about impact risks or institutional conspiracies generate more engagement than measured discussions of probability distributions and detection limitations. Resource allocation decisions at space agencies reflect broader institutional challenges in balancing immediate operational needs against long-term capability development within constrained budgets. Detecting and tracking near-Earth objects requires sustained investment in survey telescopes, data processing infrastructure, and specialized personnel whose expertise develops over decades of experience. Current detection capabilities represent accumulated investments spanning multiple generations of astronomers and engineers who built systems based on threat assessments that may no longer reflect contemporary realities. Upgrading these systems to address newly recognized vulnerabilities requires long-term commitments, extending beyond typical political cycles while competing with other priorities for limited resources. The approaching operational deployment of next-generation survey systems promises revolutionary improvements in detection rates and characterization capabilities. The Vera Rubin Observatory will scan the entire visible sky every few nights with unprecedented sensitivity, discovering objects at rates that dwarf current surveys while providing rapid follow-up capabilities for newly detected threats. However, even these advanced systems inherit fundamental limitations that affect all ground-based observations. Objects approaching from solar directions remain invisible regardless of technological sophistication, creating persistent gaps in detection coverage that space-based systems could potentially address through international cooperation and sustained funding commitments. The scientific knowledge gained from studying R2 during its current passage will influence detection strategies and risk assessment methodologies for decades to come. Every measurement of composition, structure, and behavior provides crucial data for understanding how ancient comets evolve during rare returns to the inner solar system after millennia of dormancy. These observations race against changing geometric relationships that affect observing conditions in ways that either enhance or degrade our ability to extract meaningful information. Solar elongation angles shift daily, phase relationships evolve, and brightness levels fluctuate according to complex interactions between distance, activity level, and viewing geometry that can't be predicted with perfect accuracy. The institutional flexibility required for rapid response scenarios exposes organizational limitations that extend beyond technological constraints into procedural and bureaucratic factors. Professional telescopes typically require months of advanced planning, with proposal deadlines occurring seasons before actual observations. Emergency procedures exist but must compete with established research priorities for limited telescope access. The peer review processes that ensure scientific quality and fair resource allocation become obstacles when time constraints demand immediate action based on preliminary data and uncertain threat assessments. The careful deliberation that normally characterizes astronomical research becomes a liability when rapid decisions could determine whether critical observations succeed or fail. As October 20th approaches, with each passing day reducing our observational window, the astronomical community confronts a fundamental examination of our preparedness for cosmic surprises. The compressed timeline between discovery and closest approach tests every aspect of our detection network, from automated algorithms to human decision-making processes to international cooperation mechanisms. The lessons emerging from this encounter will either validate our current approaches to planetary defense or expose critical weaknesses that demand immediate attention and resources. Whether we learn the right lessons could determine how effectively we respond to the next unexpected visitor from the outer darkness, whenever and however it chooses to announce its presence. The mathematical precision of orbital mechanics provides comforting certainty in an uncertain universe, but that precision depends entirely on complete and accurate input data. When objects arrive with minimal observational histories and uncertain physical properties, even the most sophisticated computational models produce results hedged with statistical uncertainties, encompassing wide ranges of possible outcomes. These mathematical limitations compound when considering the broader population of similar objects that may be approaching through detection gaps we're only beginning to recognize. R2's late discovery suggests current statistical models may significantly underestimate true numbers of potentially hazardous visitors, transforming our risk calculations from reliable assessments into mathematical exercises based on incomplete information. The cascade of consequences flowing from delayed detection extends through every layer of modern civilization's technological infrastructure. From communication satellites enabling global commerce to navigation systems guiding aircraft and ships, to military assets providing national security, our orbital environment hosts hundreds of billions of dollars in critical infrastructure potentially vulnerable to debris clouds our detection systems might miss. The emergence of private space industries adds new dimensions to these vulnerability calculations, with commercial satellite constellations deploying thousands of spacecraft into low Earth orbit at unprecedented rates. Each new satellite represents both an additional target for potential debris impacts and a potential source of secondary debris if destroyed by high-velocity particles. The space debris environment has already reached critical density levels in some orbital regions, where cascade effects could trigger runaway collision sequences that render entire altitude bands unusable for future missions. Adding thousands of new fragments from a disintegrating comet could accelerate these cascade scenarios while overwhelming tracking systems designed for much smaller object populations. Ground-based infrastructure faces different but equally serious vulnerabilities despite atmospheric protection from smaller particles. The 2013 Chelyabinsk event demonstrated how even modest-sized objects can cause widespread damage when entering the atmosphere over populated areas, with blast effects shattering windows across hundreds of square kilometers and injuring over 1,000 people. That incident arrived without advance warning, approaching from the sun's direction where ground-based surveys couldn't detect it until atmospheric entry began. The parallels to R2's detection challenges highlight persistent blind spots in our surveillance network that could leave populated areas vulnerable to similar surprise encounters. The international legal frameworks governing space activities weren't designed for scenarios involving fragmenting objects with uncertain ownership and liability chains. If debris pieces damage infrastructure or cause injuries, determining responsibility and compensation could involve unprecedented legal challenges that current space law doesn't adequately address through existing treaty mechanisms. The economic modelling required for insurance and risk management purposes struggles with distributed threats involving uncertain fragment numbers, unknown trajectory dispersions, and statistical impact probabilities that can't be calculated using historical precedents. Traditional actuarial approaches assume well-defined risks with established frequency distributions that don't exist for fragmenting comet scenarios. The communication challenges surrounding R2's approach reveal fundamental tensions between scientific uncertainty and public information needs. Authoritative sources appropriately emphasize measurement limitations and probability ranges, but these nuanced messages compete with sensationalized content optimized for social media engagement rather than educational accuracy. The compressed timeline between discovery and closest approach provides insufficient opportunity for the peer review and consensus-building processes that normally filter scientific conclusions before public dissemination. Preliminary results must be communicated while acknowledging significant uncertainties that may not be resolved until after the critical encounter period ends. Educational opportunities created by public interest in R2's passage face institutional constraints that prevent comprehensive curriculum development or coordination with planetariums and science museums. The rapid evolution of understanding about the object's properties and behavior makes it difficult to create stable educational content that remains accurate throughout the encounter timeline. The amateur astronomy community's response demonstrates both the potential and limitations of distributed observational networks in supplementing professional capabilities. Dedicated observers contribute valuable monitoring coverage across multiple time zones and weather systems, but varying calibration standards create data validation challenges that consume precious analysis time. The technological infrastructure supporting modern astronomical surveys operates near capacity limits that could be overwhelmed by sudden increases in object detection rates. Adding thousands of new fragments requiring individual tracking and orbital calculations would strain computational resources while demanding communication bandwidth that exceeds current network capabilities. The institutional memory required for effective crisis response includes expertise that develops over decades of experience with rare but critical events. As veteran astronomers retire and institutional knowledge transfers to new generations, the accumulated wisdom about handling unusual situations could be lost if not properly documented and preserved. The policy implications of improved detection capabilities include questions about information sharing, public notification, and response coordination that haven't been fully resolved through existing international agreements. Different nations may reach different conclusions about the same observational data, potentially leading to conflicting public messages about risk levels and appropriate precautions. The philosophical dimensions of planetary defense extend beyond technical capabilities into fundamental questions about humanity's relationship with the cosmic environment. Whether we view ourselves as passive victims of celestial mechanics or active participants capable of influencing outcomes determines how aggressively we invest in detection, negation technologies, and EMIT. As R2 continues its final approach toward the October 20th encounter, every night of observations adds crucial data points, while the window for comprehensive characterization narrows. The knowledge gained from this passage will inform detection strategies, risk assessment methodologies, and international cooperation frameworks for decades of future planetary defense efforts. The broader implications transcend this single object to encompass our entire approach to cosmic hazard mitigation. Whether the lessons learned validate current systems or expose critical weaknesses will influence funding priorities, technology development programs, and policy decisions affecting humanity's long-term survival in an inherently dangerous cosmic neighborhood. The detection network we've constructed represents humanity's first systematic attempt to monitor our cosmic environment for potential threats. But R2's late discovery reveals how much we still don't know about the population of objects sharing our solar system. The statistical models underlying our risk assessments depend on assumptions about detection completeness that may be fundamentally flawed. The next few days will test every component of our observational infrastructure while providing crucial data about an object that nearly escaped our notice entirely. Whether we emerge from this encounter with confidence in our capabilities or recognition of their limitations will shape planetary defense strategies for generations of future cosmic guardians tasked with protecting Earth from the unexpected visitors lurking in the darkness beyond our current vision. The technological sophistication required to monitor thousands of potential debris fragments simultaneously pushes our current computational infrastructure beyond its design limits. Modern orbital mechanics calculations that seem routine for single objects become exponentially complex when applied to fragment clouds, where each piece requires individual trajectory modeling, uncertainty, propagation, and collision probability assessment updated in real time as new observations arrive. The database systems storing our current catalogue of tracked objects weren't architected to handle sudden influxes of thousands of new entries appearing within days or weeks. Adding fragment populations from a single disintegrating comet could overwhelm storage capacity, processing pipelines, and data distribution networks that took decades to develop and optimize for much smaller object populations. The human element in this technological chain faces equally severe stress testing when confronted with scenarios that exceed normal operational parameters. Orbital analysts trained to track predictable satellites and well-characterized asteroids must suddenly adapt to monitoring chaotic fragment distributions with uncertain physical properties and evolving trajectories that don't follow established patterns. The decision-making protocols governing space traffic management assume clear ownership chains and predictable orbital behavior that disappear when dealing with naturally fragmenting objects. No single nation or organization owns a disintegrating comet, yet the debris it produces could threaten assets belonging of countries operating to dozens of satellites in affected orbital regions. Current space law provides limited guidance for scenarios where natural phenomena create widespread hazards affecting multiple national interests simultaneously. The liability frameworks developed for satellite collisions and debris creation assume human actors making deliberate decisions, not random cosmic events producing thousands of uncontrolled fragments with uncertain impact probabilities. The insurance mechanisms protecting satellite operators against collision risks rely on actuarial models, calibrated for well-understood threat populations with historical precedents. Fragmenting comets create entirely new risk categories that exceed the mathematical frameworks currently used for commercial space insurance, potentially leaving billions of dollars in orbital assets effectively uninsurable against novel hazard types. The cascading economic effects extend far beyond direct satellite replacement costs into the broader infrastructure dependencies that modern civilization takes for granted. Global positioning systems, communication networks, weather forecasting, financial transaction processing, and military command structures all rely on orbital assets that could be compromised by dense debris clouds intersecting critical orbital regions. The redundancy measures built into these systems provide some protection against individual satellite failures, but they weren't designed to handle simultaneous impacts affecting multiple spacecraft across different orbital planes and altitude ranges. The distributed nature of fragment clouds creates correlation risks that could overwhelm backup systems designed for independent failure modes. The atmospheric entry scenarios for larger fragments introduce additional complexity layers that challenge current impact assessment methodologies. While smaller particles burn up harmlessly during atmospheric passage, objects larger than a few meters can survive to reach the surface, with significant kinetic energy depending on approach angle, velocity, and structural properties. The unpredictability of atmospheric breakup processes means that even fragments with similar initial sizes might produce vastly different ground effects, depending on composition, internal structure, and entry dynamics. Some might explode at high altitude, creating airbursts that damage structures across wide areas, while others could survive intact to create localized but intense impact craters. The population distribution patterns beneath potential impact zones introduce demographic variables that dramatically affect casualty and damage estimates. A fragment entering over uninhabited ocean areas poses minimal direct risk to human life, while identical objects approaching populated regions could cause thousands of casualties and billions in property damage. The warning systems designed to alert populations about incoming meteoroids operate on timescales measured in minutes or hours, assuming detection occurs while objects are still in space and trackable by radar systems. Fragment clouds with hundreds of pieces following slightly different trajectories could overwhelm notification systems while making it impossible to provide specific impact predictions for individual communities. The emergency response protocols developed for natural disasters typically assume localized events affecting specific geographic regions where resources can be concentrated and coordinated. Multiple simultaneous impacts scattered across continents would strain emergency management systems beyond their designed capacity, while creating coordination challenges that exceed current international disaster response frameworks. The scientific opportunities presented by studying an active fragmentation event in real time offer unprecedented insights into comet structure and behavior that could inform future hazard assessment methodologies. Every observation of how R2 responds to solar heating and tidal stress adds crucial data points to our understanding of how similar objects might behave during future close approaches. The spectroscopic analysis of outgassing materials provides direct evidence about internal composition and volatile distribution patterns that remain invisible until activated by solar energy. These measurements help distinguish between different formation scenarios while constraining models of how ancient comets evolved during their long journeys through the outer solar system. The photometric monitoring of brightness variations reveals information about rotation states, surface heterogeneity, and activity patterns that could indicate structural instabilities or fragmentation precursors. Amateur astronomers contributing continuous coverage across multiple time zones often catch transient events that scheduled professional observations might miss entirely. The astrometric measurements, tracking R2's position against background stars with increasing precision as more observations accumulate, will either confirm current orbital predictions or reveal deviations that indicate non-gravitational forces affecting the trajectory. These subtle accelerations from asymmetric outgassing could shift the closest approach distance by thousands of kilometers. The radar observations attempting to directly range the comet face significant technical challenges due to R2's distance and relatively small size, but successful measurements could provide definitive constraints on nucleus dimensions and rotation characteristics that remain uncertain from optical observations alone. The international coordination required for effective multi-site observations tests, cooperation mechanisms that normally operate over much longer timescales and less urgent circumstances. Sharing data rapidly across different institutions while coordinating observation schedules across time zones requires infrastructure and protocols originally designed for routine scientific collaboration rather than crisis response scenarios. The communication challenges facing astronomers trying to convey complex uncertainties to diverse audiences highlight fundamental tensions between scientific honesty about measurement limitations and public desires for definitive answers about potential risks. The compressed timeline between discovery and closest approach provides minimal opportunity for the careful consensus building that normally characterizes major astronomical announcements. The media coverage pattern surrounding R2's approach demonstrate both the potential and limitations of modern science communication, during rapidly evolving situations. Accurate information about orbital mechanics and probability distributions must compete with sensationalized content, optimized for social media engagement, rather than educational accuracy or nuanced understanding. The educational institutions attempting to incorporate R2's passage into curricula and outreach programming face logistical constraints that prevent comprehensive material development or coordination with planetariums and science museums. The rapid pace of discovery and characterization makes it difficult to create stable educational content that remains accurate throughout the encounter timeline. The amateur astronomy community's mobilization to contribute observations using backyard telescopes and imaging systems represents a remarkable example of citizen science responding to urgent scientific needs. This distributed network provides monitoring capabilities that complement professional facilities while demonstrating public engagement with cosmic hazard awareness. The data validation challenges created by varying calibration standards across amateur observation networks require careful analysis to distinguish reliable measurements from problematic data points that could introduce errors into orbital calculations. The time constraints surrounding R2's approach limit opportunities for thorough quality assessment of contributed observations. The computational resources required for processing increasing volumes of observational data approach the limits of available systems designed for much smaller data flows and less time-critical analysis requirements. The rapid cadence of observations needed for accurate trajectory refinement creates processing backlogs that could delay crucial orbital updates. The archive systems storing astronomical observations weren't designed for the high-frequency data streams generated during intensive monitoring campaigns, focusing on rapidly moving objects. The storage and retrieval capabilities optimized for routine survey operations struggle with the specialized requirements of crisis response scenarios. The software systems managing telescope scheduling and observation planning face unprecedented demands when multiple facilities worldwide attempt to coordinate observations of the same target with rapidly changing observing conditions. The algorithms optimizing telescope usage for normal scientific operations may not adapt effectively to emergency scheduling requirements. The weather forecasting capabilities supporting astronomical observations provide limited accuracy for the week-to-week predictions needed to plan critical observation campaigns. Cloud cover, atmospheric turbulence, and precipitation patterns can't be predicted with sufficient precision to guarantee observational success during narrow windows when R2 remains optimally positioned for study. The backup systems and contingency plans developed for individual observatory failures don't address scenarios where systematic factors like weather or geometric constraints simultaneously affect multiple facilities. The redundancy built into professional networks assumes independent failure modes rather than correlated problems affecting entire observation campaigns. The quality control procedures ensuring measurement accuracy and calibration stability face compression under the rapid pace of observations required for effective R2 monitoring. The careful validation processes that normally characterize professional astronomy must be accelerated while maintaining sufficient rigor to support critical risk assessments. The peer review mechanisms that validate scientific conclusions before publication struggle with the compressed timelines demanded by rapidly evolving situations where preliminary results must be communicated despite significant remaining uncertainties. The balance between scientific caution and timely information sharing becomes particularly challenging during potential crisis scenarios. The funding mechanisms supporting planetary defense research operate on annual budget cycles that can't respond rapidly to unexpected discoveries, requiring immediate resource allocation. The institutional flexibility needed for surge capacity during crisis scenarios may not exist within current organizational structures designed for predictable long-term research programs. The personnel resources available for intensive monitoring campaigns represent accumulated expertise developed over decades of experience with rare but critical events. The specialized knowledge required for effective comet characterization and risk assessment exists within relatively small communities of researchers whose time and attention become precious resources during encounters like R2's approach. The international agreements governing data sharing and cooperation in planetary defense scenarios provide general frameworks but lack specific protocols for handling rapidly developing situations where time constraints limit opportunities for extensive consultation and consensus building among participating nations and institutions. The legal frameworks addressing liability and responsibility for space-related hazards assume scenarios involving human actors making deliberate decisions rather than natural phenomena, creating widespread risks affecting multiple national interests simultaneously. The precedents established during R2's encounter could influence how future cosmic hazard scenarios are managed legally and politically. The technological development programs aimed at improving detection and characterization capabilities operate on timescales measured in years or decades, making them poorly suited for addressing immediate shortcomings revealed by current events. The lessons learned from R2's passage may not translate into improved capabilities until long after this particular encounter concludes. The institutional memory required for effective crisis response includes accumulated wisdom about managing unusual situations that may not be adequately documented or transferred between generations of researchers. As experienced astronomers retire and new personnel assume responsibilities, critical knowledge about handling exceptional cases could be lost if not properly preserved. As we approach the final days before R2's October 20th closest approach, every remaining precious for advancing observation becomes increasingly our understanding of this enigmatic visitor that nearly escaped detection entirely. The compressed timeline forces difficult decisions about resource allocation and observation priorities that will determine how much we learn from this rare opportunity. The data collected during these final weeks will either validate our current detection and assessment capabilities or expose fundamental weaknesses that demand immediate attention and implications extend resources, the hazard mitigation, and far beyond this single object. The mathematical planetary defense strategy to encompass our entire approach to cosmic models, predicting R2's behavior, uncertainty margins that reflectees could encompass during closest approach, carry both measurement limitations and incomplete understanding of comet physics. These uncertain outcomes ranging from completely to scenarios requiring immediate attention from space agencies and emergency uneventful passage management organizations. The observation ever directed toward a potential encounter period represent hazardous object discovered with campaigns planned for the critical. The success or the most intensive monitoring effort, how future similar failure of these efforts will influence such short notice, TWO's unexpect providing crucial data for improving detection and response capabilities. The lessons emerging at appearance and challenging we learn situations are handled while from our characterization will inform planetary defense strategies for decades to come. Whether darkness beyond our current observed the right lessons could determine how effectively humanity responds to the next cosmic surprise lurking in the expose. The detection gap sational reached by R2's late discovery suggests that our statistical models of Earth object the near population may be fundamentally incomplete, with implications that cascade through every aspect of risk assessment and resource allocation for planetary defense. If objects like R2 represent a significant fraction of the true threat population, our current protection levels may be far lower than we believe. The technological and institutional responses to this encounter will establish precedents for handling future cosmic visitors that arrive with minimal warning and uncertain characteristics. The coordination mechanisms, communication protocols, and decision-making frameworks developed during the next few days could determine whether humanity emerges better, prepared for the inevitable next surprise from the vast cosmic wilderness surrounding our small planetary home. The cascade failures rippling through our detection infrastructure reveal something far more unsettling than a single missed comet. They expose a fundamental philosophical problem disguised as a technical limitation. We've constructed our entire planetary defense network around the comfortable assumption that cosmic threats will announce themselves politely, arriving from predictable directions with predictable characteristics that conform to our mathematical models and observational conventions. R2's late discovery shatters this assumption completely. Here was an object that violated every rule in our detection playbook. It approached from solar direction where our telescopes cannot look. It remained dormant during its inbound journey, producing no visible coma or tail to betray its presence. It brightened suddenly after perihelion, when most surveys had already moved their attention elsewhere. It was discovered not by our sophisticated automated systems, but by an amateur astronomer analyzing spacecraft data never intended for comet hunting. This represents more than a detection failure. It represents a catastrophic blind spot in our understanding of what cosmic hazards actually look like when they're trying to kill us. The most dangerous objects aren't the well-behaved visitors that follow predictable orbits and brightness curves. They're the rule breakers, the anomalies, the cosmic guerrilla fighters that exploit every weakness in our surveillance network. Consider the mathematics of this vulnerability. Current risk models assume we've detected roughly 90% of near-Earth asteroids larger than 1 kilometre diameter. This statistic gets repeated endlessly in scientific papers and policy documents as evidence of our detection completeness. But that 90% figure is based on statistical extrapolations from observed populations. If our detection methods systematically miss entire categories of objects, those extrapolations become exercises in mathematical self-deception. The algorithm problem runs deeper than most people realize. Modern survey telescopes generate such enormous volumes of data that human review of every detection becomes impossible. We're completely dependent on automated systems that make decisions every night, thousands of classification, sorting celestial objects into categories like star, galaxy, asteroid, or instrumental artifact. These digital gatekeepers operate according to rules we've programmed based on our understanding of how different types of objects should behave. But what happens when an object doesn't behave as expected? When a comet approaches without visible activity? When brightness levels fluctuate outside programmed parameters? When motion patterns don't match training data? The algorithms do exactly what they were designed to do. They classify anomalous objects as noise and filter them out of the detection pipeline. The most threatening visitors become invisible not because our instruments can't see them, but because our software doesn't recognize them as real. This creates a terrifying feedback loop where the objects most likely to surprise us are precisely those most likely to be dismissed by our automated systems. The rule followers get detected and catalogued. The rule breakers disappear into digital oblivion, erased by algorithms that mistake genuine anomalies for instrumental artifacts. The weather dimension adds another layer of vulnerability that compounds during critical observation windows. October weather patterns across major observatory sites bring increased cloud cover, seasonal atmospheric turbulence, and changing daylight hours that can eliminate entire nights of potential observations. When you're dealing with an object discovered just weeks before closest approach, losing even a single clear night to weather can mean missing crucial characterization data forever. Professional observatories have backup sites and international coordination networks designed to provide redundancy against local weather problems. But these systems assume routine observations that can be rescheduled if conditions aren't optimal. They weren't designed for crisis scenarios where every clear hour becomes precious and irreplaceable. The logistics of coordinating rapid target of opportunity observations across multiple continents in real time pushes these networks beyond their operational limits. Space-based telescopes offer weather-independent observations, but they introduce different constraints that can be equally limiting. The Hubble Space Telescope and James Webb Space Telescope provide exquisite sensitivity and resolution when properly targeted, but their narrow fields of view and extremely limited observing time make them unsuitable for continuous monitoring campaigns. Getting target of opportunity time on these flagship missions requires competing against other urgent scientific priorities while navigating bureaucratic approval processes that can consume days or weeks. The amateur astronomy community has emerged as an unexpected critical component of our detection network, with dedicated observers using to provide backyard equipment, continuous monitoring capabilities that professional facilities cannot match. This distributed surveillance system operates across multiple time zones and weather patterns, often catching transient events that scheduled institutional observations miss entirely. During R2's approach, amateur astronomers with modest telescopes and digital cameras have contributed observations that complement billion-dollar space missions. However, the varying quality and calibration standards across amateur networks create data validation challenges that consume precious analysis time. While many serious observers maintain equipment and techniques approaching professional standards, others produce measurements with significant uncertainties that require careful evaluation before incorporation into critical orbital calculations. The time pressure surrounding R2's encounter limits opportunities for thorough quality assessment of contributed observations. The computational infrastructure supporting modern astronomical surveys operates near capacity limits that could be overwhelmed by sudden increases in detection rates. The database systems storing our current catalogue of tracked objects weren't architected to handle influxes of thousands of new entries appearing within days or weeks. If R2 fragments and creates a debris field, adding those pieces to existing tracking systems could overwhelm storage capacity, processing pipelines, and data distribution networks that took decades to optimize for much smaller object populations. The human element in this technological chain faces equally severe stress testing when normal operational parameters get exceeded. Orbital analysts trained to track predictable satellites and well-characterized asteroids must suddenly adapt to monitoring chaotic situations with uncertain physical properties and evolving trajectories that don't follow established patterns. The expertise required for effective comet characterization exists within relatively small communities of researchers whose time and attention become precious resources during encounters like R2's approach. The international coordination mechanisms that enable global scientific cooperation operate on timescales much longer than crisis response scenarios demand, sharing sensitive observational data across national boundaries, coordinating telescope schedules across different institutions, and maintaining communication during rapidly evolving situations requires infrastructure and protocols originally designed for routine scientific collaboration rather than urgent planetary defense applications. The communication challenges facing astronomers trying to convey complex uncertainties to diverse audiences highlight fundamental tensions between scientific honesty about measurement limitations and public expectations for definitive answers about potential risks. The compressed timeline between R2's discovery and closest approach provides minimal opportunity for the careful peer review and consensus-building processes that normally characterize major astronomical announcements. Media coverage patterns demonstrate how sensationalized content optimized for social media engagement competes with accurate information about orbital mechanics and probability distributions. Dramatic headlines about approaching cosmic threats generate more clicks and shares than nuanced discussions of statistical uncertainties and detection limitations. This creates information environments where genuine scientific understanding gets buried beneath layers of speculation and sensationalism. The economic modeling required for insurance and risk management purposes struggles with distributed threats involving uncertain fragment numbers, unknown trajectory dispersions, and impact probabilities that can't be calculated using historical precedents. The satellite industry represents hundreds of billions of dollars in orbital infrastructure, but traditional actuarial approaches assume well-defined risks with established frequency distributions that don't exist for fragmenting comet scenarios. Current space law provides limited guidance for scenarios where natural phenomena create widespread hazards affecting multiple national interests simultaneously. The liability frameworks developed for satellite collisions assume human actors making deliberate decisions, not random cosmic events producing thousands of uncontrolled fragments with uncertain ownership chains and impact probabilities. The emergency response protocols developed for natural disasters typically assume localized events affecting specific geographic regions where resources can be concentrated and coordinated. Multiple simultaneous impacts scattered across continents would strain emergency management systems beyond their designed capacity, while creating coordination challenges that exceed current international disaster response frameworks. The technological development programs aimed at improving detection capabilities operate on timescales measured in years or decades, making them poorly suited for addressing immediate shortcomings revealed by current events. The lessons learned from R2's passage may not translate into improved capabilities until long after this particular encounter concludes, leaving us vulnerable to similar detection failures in the interim. The approaching deployment of next-generation survey systems promises revolutionary improvements in detection rates and characterization capabilities. The Vera Rubin Observatory will scan the entire visible sky every few nights with unprecedented sensitivity, discovering objects at rates that dwarf current surveys. However, even these advanced systems geometric inherit fundamental limitations that affect all ground-based observations. Objects approaching from solar directions will remain invisible regardless of technological sophistication. Space-based detection systems offer solutions constraints to geometric, but require international cooperation, sustained funding commitments, and technological development programs spanning decades from concept to operational deployment. The barriers to implementing comprehensive space-based surveillance exceed current institutional capabilities while demanding coordination across nations that may have competing strategic interests. The philosophical dimensions of planetary defense extend beyond technical capabilities into fundamental questions about humanity's relationship with the cosmic environment. Whether we view ourselves as passive victims of celestial mechanics or active participants capable of influencing outcomes determines how aggressively we invest in detection and mitigation technologies. The choice between fatalistic acceptance and proactive defense shapes every policy decision about resource allocation and international cooperation. The statistical models underlying our risk assessments depend critically on assumptions about detection completeness that may be fundamentally flawed. If systematic biases in our observation methods cause us to miss entire categories of objects, our probability calculations become exercises in mathematical fiction rather than reliable hazard assessments. The comfortable certainty of our current threat models may be built on foundations of incomplete data and wishful thinking. The cascade effects of improved detection capabilities include questions about information sharing, public notification, and response coordination that haven't been fully resolved through existing international agreements. Different nations may reach different conclusions about identical observational data, potentially leading to conflicting public messages about risk levels and appropriate precautions during crisis scenarios. The institutional memory required for effective crisis response includes accumulated wisdom about managing unusual situations that may not be adequately documented or transferred between generations of researchers. As experienced astronomers retire and new personnel assume responsibilities, critical knowledge about handling exceptional cases could be lost if not properly preserved and transmitted. The quality control procedures, ensuring measurement accuracy and calibration stability, face compression under the rapid pace of observations required for effective monitoring campaigns. The careful validation processes that normally characterize professional astronomy must be accelerated while maintaining sufficient rigor to support critical risk assessments and orbital predictions. The peer review mechanisms that validate scientific conclusions before publication struggle with compressed timelines where preliminary results must be communicated despite significant remaining uncertainties. The balance between scientific caution and timely information sharing becomes particularly challenging when potential crisis scenarios demand immediate attention from decision-makers. The funding mechanisms supporting planetary defense research operate on annual budget cycles that can't respond rapidly to unexpected discoveries, requiring immediate resource allocation. The institutional flexibility needed for surge capacity during crisis scenarios may not exist within current organizational structures designed for predictable, long-term research programs rather than emergency response operations. As R2 continues its final approach toward October 20th, every remaining night of observations becomes increasingly precious for advancing our understanding of this enigmatic visitor that nearly escapes detection entirely. The data collected during these critical weeks will either validate our current detection and assessment capabilities or expose fundamental weaknesses demanding immediate attention and resources. The broader implications extend far beyond this single object to encompass our entire philosophical approach to cosmic hazard mitigation. Whether the lessons learned validate current systems or expose critical vulnerabilities will influence funding priorities, technology development programs, and international cooperation frameworks for generations of future planetary defenders tasked with protecting Earth from the unexpected visitors lurking in the darkness beyond our current vision. The mathematical precision of orbital mechanics provides comforting certainty in an uncertain universe, but that precision depends entirely on complete and accurate input data. When objects arrive with minimal observational histories and uncertain physical properties, even the most sophisticated computational models produce results hedged with statistical uncertainties that could encompass drastically different outcomes. These mathematical limitations compound when considering the broader population of similar objects that may be approaching through detection gaps we're only beginning to recognize. The detection network we've constructed represents humanity's first systematic attempt to monitor our cosmic environment for potential threats, but R2's late discovery reveals how much we still don't understand about the population of objects sharing our solar system. The next few days will test every component of our observational infrastructure while providing crucial data about an object that nearly escaped our notice entirely. Whether we emerge from this encounter with confidence in our capabilities or recognition of their limitations will shape planetary defense strategies for generations of cosmic guardians charged with protecting our small world from the vast wilderness of space. The atmospheric entry calculations reveal scenarios that should terrify every emergency management official on the planet. When fragments from R2 begin their final descent through Earth's protective shell of gases, the physics governing their survival becomes a deadly lottery where size, composition, and approach angle determine whether we face harmless light shows or catastrophic ground impacts. Objects smaller than a few meters typically disintegrate completely during atmospheric passage, creating brilliant meteors that pose no surface threat. But the boundary between harmless and hazardous isn't sharp. It's a fuzzy zone where slight differences in structural integrity or entry velocity can mean the difference between spectacular fireworks and city-destroying explosions. The 2013 Chelyabinsk meteor illustrates this uncertainty perfectly. At roughly 20 meters diameter, it should have been manageable according to most atmospheric entry models. Instead, it exploded with energy equivalent to several hundred kilotons of TNT, shattering windows across an entire metropolitan area and injuring over 1,000 people. The blast wave travelled for hundreds of kilometers, demonstrating how even modest-sized objects can cause widespread damage when atmospheric physics doesn't cooperate with theoretical predictions. Now, imagine dozens of Chelyabinsk-sized fragments entering the atmosphere simultaneously across continents. Emergency different designed for single response systems, point disasters would face coordination nightmares that exceed every existing protocol. How do you evacuate multiple cities when you can't predict which ones face impact threats? How do you coordinate international disaster response when fragments could strike anywhere within thousands of square kilometers? The warning systems designed to alert populations about incoming meteoroids operate on timescales measured in minutes, assuming detection occurs while objects remain trackable by radar systems. Fragment clouds containing hundreds of pieces following slightly different trajectories could overwhelm notification infrastructure, while making specific impact predictions impossible for individual communities. Current emergency management frameworks assume localized events where resources can be concentrated and coordinated effectively. Multiple simultaneous impacts scattered across continents would strain these systems beyond their design capacity, while creating communication bottlenecks that could delay critical response efforts during the crucial first hours after impact. The medical infrastructure implications become particularly sobering when considering blast wave effects across urban areas. The Chelyabinsk event sent over 1,000 people to hospitals, primarily from flying glass and debris caused by shockwave overpressure. Scale this up to multiple cities simultaneously, and you quickly exceed available emergency medical capacity across entire regions. Insurance markets struggle to quantify these distributed risks using actuarial models designed for well-defined, historically precedented hazards. The global property damage from multiple airbursts could reach hundreds of billions of dollars, but calculating premiums requires statistical frameworks that don't exist for fragmenting comet scenarios. Traditional risk assessment assumes single-point events with known probability distributions, not chaotic fragment dispersals with uncertain impact patterns. The agricultural implications deserve serious consideration given the timing of R2's approach during critical harvest seasons across both hemispheres. Airbursts over farmland might not cause direct casualties, but blast effects could destroy crops across thousands of square kilometers, while contaminating soil with meteoritic material that affects future growing seasons. Transportation networks face vulnerabilities that cascade through entire economic systems when multiple impact zones require simultaneous emergency response. Airports could be closed across vast regions due to atmospheric debris, while highways and rail lines suffer damage that isolates affected communities from outside assistance during critical recovery periods. The power grid infrastructure represents another critical vulnerability point, where blast effects from airbursts could trigger cascading failures across interconnected electrical networks. Modern power systems are designed with redundancy for routine equipment failures, but they weren't engineered to handle simultaneous damage across multiple nodes caused by atmospheric explosions. Communication systems essential for emergency coordination could be compromised by electromagnetic effects from multiple airbursts occurring within short time periods. The ionospheric disturbances created by high-energy atmospheric explosions can disrupt radio communications across vast areas, making coordination between emergency response teams extremely difficult. The psychological impact of multiple simultaneous atmospheric events would create panic reactions that complicate emergency response efforts regardless of actual physical damage. Populations witnessing brilliant fireballs and hearing explosive sounds from atmospheric breakups might assume nuclear attacks or other deliberate threats, leading to evacuation behaviors that overwhelm transportation systems. Social media amplification of fragmentary information during chaotic, multi-impact scenarios could spread misinformation faster than official emergency communications reach affected populations. Videos of atmospheric explosions and impact damage shared without context might trigger panic responses in regions facing no actual danger, while hindering effective response in areas that genuinely need assistance. The international coordination challenges multiply exponentially when dealing with impacts across multiple national boundaries. Different countries maintain separate emergency response protocols, communication systems, and resource allocation frameworks that weren't designed for simultaneous activation during transnational disaster scenarios. Military assets often provide crucial support during large-scale natural disasters, but multiple simultaneous impact zones could exhaust available helicopter, transport, and logistics capabilities while creating competing demands for resources across different national command structures. The scientific opportunities presented by multiple atmospheric entry events would be unprecedented, providing data about fragment composition, structural properties, and breakup dynamics that could inform future hazard assessment methodologies. However, the chaos of emergency response operations might prevent effective data collection during the critical minutes when fragments interact with Earth's atmosphere. Ground-penetrating radar and seismic monitoring networks could provide valuable information about fragment impacts and underground damage patterns, but only if the sensor infrastructure survives blast effects and maintains communication links during the immediate aftermath of multiple events. The forensic analysis of impact sites and recovered meteoritic material would require coordination between scientific institutions and emergency response agencies during periods when access to affected areas might be restricted for safety or security reasons. Preserving valuable scientific evidence while addressing immediate human needs creates competing priorities that emergency management protocols don't adequately address. The environmental impact assessment for multiple fragment impacts extends beyond immediate blast damage into long-term effects on ecosystems, water supplies, and atmospheric chemistry. Meteoritic material contains trace elements and compounds that could accumulate in affected areas, requiring monitoring programs that persist for years after initial impact events. Climate modelling suggests that multiple large airbursts occurring within short significant amounts of dust time periods could inject and aerosols into the upper atmosphere, potentially affecting regional weather patterns and agricultural productivity for months or years following the initial events. The economic recovery timeline for regions affected by multiple fragment impacts would likely extend for decades, particularly in areas where critical infrastructure suffers simultaneous damage across multiple systems. The cascading effects of transportation, communication, and power grid disruptions could amplify direct impact damage by orders of magnitude. Insurance claim processing for distributed impact scenarios would strain legal and financial systems designed to handle individual events with clear cause and effect relationships. When hundreds of fragments create thousands of separate damage incidents across multiple countries, determining coverage and liability becomes an administrative nightmare that could take years to resolve. The precedents established during R2's encounter could influence how future fragmenting Comet scenarios are managed legally, economically, and politically. The international agreements governing disaster response, scientific data sharing, and liability allocation may need fundamental revision to address the unique challenges posed by distributed cosmic hazards. The lessons learned from emergency response coordination during this encounter will inform planning for future scenarios involving multiple simultaneous impact zones. Whether current frameworks prove adequate or require complete restructuring depends on how effectively institutions adapt to challenges that exceed every existing protocol. The technological infrastructure supporting impact monitoring and damage assessment faces unprecedented demands when dealing with multiple simultaneous events across vast geographic areas. Satellite imagery, aerial reconnaissance, and ground-based sensor networks must coordinate to provide comprehensive situational awareness during chaotic conditions where normal communication systems may be compromised. The data processing requirements for analyzing multiple impact zones simultaneously could overwhelm computational resources designed for single event scenarios. Emergency management agencies rely on rapid assessment tools that may not scale effectively to handle dozens of simultaneous damage zones, requiring individual evaluation and response prioritization. The personnel resources required for effective multi-impact response exceed available expertise in most emergency management systems. Specialized teams trained in meteorite impact assessment, blast damage evaluation, and atmospheric entry forensics exist in very limited numbers that would be quickly overwhelmed by scenarios involving dozens of simultaneous events. The supply chain implications for emergency response equipment and materials become critical when multiple impact zones require simultaneous support. Medical supplies, temporary shelter materials, heavy equipment for debris removal, and specialized scientific instruments must be distributed across vast areas during periods when transportation networks face their own damage and disruption. The public health monitoring required after multiple atmospheric events includes tracking respiratory effects from dust and aerosols, monitoring water supply contamination, and assessing long-term environmental exposure risks across affected populations. The distributed nature of fragment impacts creates monitoring challenges that exceed current public health surveillance capabilities. The agricultural monitoring programs necessary for assessing crop damage and soil contamination across multiple impact zones require resources and expertise that most countries maintain in limited quantities. The timing of R2's approach during harvest seasons could affect food security calculations across entire regions if multiple airbursts damage agricultural areas simultaneously. The urban planning implications for cities affected by blast damage from atmospheric explosions include decisions about rebuilding standards, evacuation route improvements, and emergency shelter requirements that reflect lessons learned from multi-impact scenarios. Building codes developed for single-event disasters may prove inadequate for situations involving multiple simultaneous blast effects. The research funding priorities for planetary defense programs will likely shift based on lessons learned from R2's encounter and the emergency response challenges it reveals. The balance between detection capabilities and impact mitigation technologies may require reassessment if current scenarios expose critical gaps in our preparedness for distributed threat events. The international treaty frameworks governing space-related hazards may need fundamental revision to address scenarios where natural phenomena create widespread damage affecting multiple nations simultaneously. Current agreements assume single-point events with clear geographic boundaries rather than distributed threats that cross national borders unpredictably. The education and training programs for emergency responders must incorporate lessons learned from multi-impact scenarios that exceed traditional disaster response frameworks. The expertise required for managing distributed cosmic hazard events doesn't currently exist within most emergency management systems, requiring new specialized training programs. The communication protocols for coordinating international response during multi-impact scenarios need development and testing before actual events occur. The complexity of managing simultaneous emergency operations across multiple countries while maintaining effective information sharing exceeds current coordination capabilities. The scientific collaboration frameworks for studying multiple impact events require advanced planning to ensure valuable data collection doesn't interfere with emergency response priorities. The balance between scientific opportunity and humanitarian needs becomes particularly challenging when rare events create competing demands for limited resources and expertise. The technology development programs aimed at improving impact detection and characterization capabilities must incorporate lessons learned about the challenges of monitoring multiple simultaneous events. Current sensor networks and data processing systems may require fundamental architectural changes to handle scenarios that exceed their design parameters. The policy implications for planetary defense resource allocation will likely shift based on R2's demonstration of how quickly single objects can become distributed threats, requiring fundamentally different response approaches. The emphasis on detection versus mitigation capabilities may require rebalancing if current scenarios reveal critical gaps in our preparedness frameworks. As we approach the final days before R2's October 20th encounter, the emergency preparedness implications of potential fragmentation scenarios demand immediate attention from disaster management agencies worldwide. The compressed timeline between discovery and closest approach provides minimal opportunity for comprehensive preparation, but essential coordination mechanisms must be activated while we still have time to implement basic protective measures. The weather forecasting capabilities supporting both astronomical observations and emergency response planning face unusual demands when dealing with events that could affect multiple regions simultaneously. Accurate predictions of atmospheric conditions become critical for both scientific characterization of R2's behavior and potential emergency response if fragmentation occurs during closest approach. The satellite monitoring systems that provide crucial data for both asteroid tracking and emergency response could face direct threats if R2 produces debris clouds that intersect Earth's orbital environment. The irony of potentially losing our monitoring capabilities just when we need them most highlights the interconnected vulnerabilities in our technological infrastructure. The international cooperation mechanisms that enable effective emergency response during natural disasters will face their most severe test if R2's passage produces multiple simultaneous impact zones requiring coordinated assistance across national boundaries. The compressed timeline for preparation adds urgency to diplomatic and logistical arrangements that normally require months of advanced planning. The lessons emerging from R2's approach and our institutional responses will influence planetary defense strategies for decades to come. Whether we learn appropriate lessons about detection limitations, emergency preparedness, and international coordination could determine how effectively humanity responds to the next cosmic surprise lurking in the darkness beyond our current observational reach. The mathematical models predicting R2's behavior during closest approach carry uncertainty margins that encompass outcomes ranging from completely uneventful passage to scenarios requiring immediate activation of emergency response systems worldwide. The next few days will determine if this probability which in spectrum becomes reality, providing crucial data for improving our understanding of both cosmic hazards and our institutional capabilities for managing them. The broader implications extend far beyond this single encounter to encompass fundamental questions about humanity's preparedness for living in a cosmic environment that remains largely unpredictable and potentially hostile. Whether we emerge from R2's passage with confidence in our detection and response capabilities or recognition of critical weaknesses will shape policy decisions and resource allocation priorities for generations of future planetary defenders. The detection infrastructure we've constructed over decades of investment and development faces its most comprehensive test during R2's final approach. The integration of professional observatories, space-based sensors, amateur astronomy networks, and emergency response systems must function seamlessly during the critical observation period, when every data point could affect risk assessments for millions of people. The communication systems linking scientific institutions with emergency management agencies require activation and testing during the final days of R2's approach. The protocols for sharing time-critical information about potential fragmentation events or trajectory changes must function effectively under the pressure of real-world crisis scenarios where delays could have catastrophic consequences. The decision-making frameworks that determine when to activate emergency response measures face unprecedented challenges when dealing with probabilistic threats involving uncertain outcomes. The balance between premature alarm and adequate preparation becomes critical when the costs of both false positives and missed warnings could be measured in lives and economic disruption. As October 20th approaches with each passing hour, reducing our observation window and preparation time, the astronomical community, emergency management agencies and policymakers worldwide confront the reality that our cosmic neighborhood contains surprises we're still learning to detect and manage. The lessons learned during the next few days will influence how effectively humanity prepares for the inevitable next visitor from the vast wilderness of space surrounding our small planetary home. The cascade of institutional failures surrounding R2's discovery reveals something that should terrify every person who looks up at the night sky and assumes someone is watching. Our planetary defense network operates like a sophisticated security system designed by engineers who assumed intruders would knock politely on the front door and wait for permission to enter. The reality proves far more disturbing. The most dangerous cosmic visitors aren't the well-behaved objects that follow predictable trajectories and announce themselves with convenient brightness curves. They're the stealth operators, the rule breakers who exploit every weakness in our surveillance architecture, while we congratulate ourselves on detecting the obvious threats. Consider the mathematics of our blindness. We've built detection systems optimized for finding objects that behave according to our expectations, that arrive from convenient directions during favorable weather conditions, that maintain steady brightness levels while following gravitational physics we can model accurately. When something violates these assumptions, when it approaches from solar direction, or brightens suddenly after our surveys have moved on, it becomes effectively invisible, despite potentially carrying enough kinetic energy to devastate entire metropolitan areas. The algorithm problem cuts deeper than most people realize. Modern sky surveys generate such enormous volumes of data that human review becomes impossible, forcing complete dependence on automated systems that classify millions of objects every night, according to programmed rules based on incomplete understanding of cosmic diversity. These digital gatekeepers excel at recognizing familiar patterns while systematically filtering out anomalies that might represent genuine hazards. The feedback loop becomes terrifying when you understand its implications. The objects most likely to surprise us are precisely those most likely to be dismissed by our automated detection systems, get catalogued and tracked. Predictable visitors with mathematical precision. Unpredictable ones disappear into digital oblivion, erased by algorithms that mistake genuine cosmic threats for instrumental noise. Weather compounds these systematic failures in ways that can eliminate critical observation opportunities entirely. October conditions across major observatory sites bring seasonal cloud cover, atmospheric turbulence, and changing daylight patterns that can cost entire nights of potential observations. When dealing with objects discovered weeks before closest approach, losing even single clear nights to meteorological conditions means missing characterization data forever. The international coordination mechanisms enabling global scientific cooperation weren't designed for crisis scenarios where every hour of delay could affect risk assessments for millions of people. Sharing sensitive observational data across national boundaries, coordinating telescope schedules between competing institutions, and maintaining effective communication during rapidly evolving situations requires infrastructure originally built for routine research rather than emergency planetary defense. Space-based observations offer some protection from weather constraints, but they introduce different operational limitations that can be equally restrictive. Premium telescope time on facilities like Hubble or Webb requires competing against other urgent scientific priorities while navigating approval processes that consume days or weeks when objects are moving at interplanetary velocities. The amateur astronomy community has emerged as an unexpected critical component of our detection network, with dedicated observers using backyard equipment to provide continuous monitoring capabilities that billion-dollar professional facilities cannot match. This distributed surveillance system across multiple time operates zones and weather patterns, often catching transient phenomena that scheduled institutional observations miss completely. However, varying quality and calibration standards across amateur networks create data validation challenges that consume precious analysis time when rapid decisions could determine whether we're facing routine passage or potential catastrophe. The expertise required for distinguishing reliable observations from problematic measurements exists within relatively small communities already stretched thin by normal operational demands. The computational infrastructure supporting modern astronomical databases operates near capacity limits that could be overwhelmed by sudden detection rate increases. Systems designed to catalogue predictable objects following stable orbits would struggle catastrophically if required to track thousands of fragments, with uncertain trajectories requiring constant orbital updates based on incomplete observational data. The human element faces equally severe stress testing when normal parameters get exceeded. Orbital analysts trained on predictable satellites and well-characterized asteroids must suddenly adapt to monitoring chaotic situations involving objects with unknown physical properties following trajectories that don't conform to established behavioral patterns. The institutional knowledge required for effective crisis management exists primarily among veteran researchers whose retirement could leave critical expertise gaps. Communication challenges multiply when attempting to convey complex uncertainties to diverse audiences expecting definitive answers about potential risks. The compressed timeline between discovery and encounter provides minimal opportunity for peer review processes that normally filter scientific conclusions before public dissemination, forcing preliminary results to be communicated while acknowledging significant uncertainties that may not be resolved until after critical events conclude. So here we are, 9 days before R2's closest approach, watching our cosmic early warning system reveal its true limitations in real time. While the world obsesses over 3I Atlas, the exotic interstellar wanderer that poses no actual threat to Earth, a genuinely concerning visitor approaches from our own solar system's backyard, nearly invisible until an amateur astronomer caught what our billion-dollar detection network missed entirely. The story of C2025 R2 isn't really about this single comet. It's about the uncomfortable truth that our planetary defense infrastructure operates more like a well-calibrated fishing net than a comprehensive security system. We catch what we're designed to catch while remaining catastrophically blind to everything that doesn't follow our observational conventions. The next time you look up at the night sky, remember that the most dangerous visitors aren't the ones making headlines. They're the ones hiding in solar glare, brightening after our surveys have moved on, approaching from angles our algorithms don't recognize as real. They're the cosmic guerrilla fighters that exploit every weakness in our surveillance network while we congratulate ourselves on tracking predictable threats. October 20th will come and go. R2 will make its closest approach at 39 million kilometers, almost certainly passing safely while providing crucial lessons about the gaps in our detection capabilities. But the broader implications will persist long after this encounter ends. Every day we don't upgrade our cosmic surveillance network is another day we remain vulnerable to the next unexpected visitor from the outer darkness. The universe doesn't announce its intentions. It doesn't follow our schedules or respect our blind spots. The only thing standing between us and cosmic surprise is the quality of our detection systems and the speed of our response. R2 has shown us that both need urgent improvement before the next visit arrives with even less warning. The monster headed for Earth next week isn't the one everyone's watching.